Okay, welcome everyone. Today we are very happy to have Suvrat from ICTS, and he's going to tell us about mass particles, especially.
Okay, so thank you very much, Vijay Chas, and everyone for organizing this talk at short notice and for coming to an additional seminar in the week. So this I should make this additional seminar. Is this an extra seminar? One of your I should make this full screen ka sakte hain? Ye presentation would be nailed.
The alternative would have been to attend the colloquium, which is this is.
Oh, I'm making you miss a colloquium. I'm so sorry about that. Okay. Well, thank you also for those who have missed the colloquium. Okay, so thank you. So I want to speak today about some old work and some new work. So the old work was in fact done with Alok, Siddharth, and Pushkal. It was a paper we put out about a couple of years ago. And also some work in progress with Athira and Anupam, who are postdocs at. So, by the way, these people you all know. Siddharth and Pushkal over here, of course, and Alok, you know. Athira and Anupam, who are current postdocs at ICTS, and Priyadarshan, who is a current student at ICTS. And this paper, we're pretty sure will be out in hopefully next week, but certainly this month. So this is the work that I want to speak of. It's some work which is still in progress. In fact, I spoke a little bit about this in December, briefly, but at that time we were just starting this project and we didn't quite have a clear picture. And now we have a much clearer picture. So some of you might remember what I said from December. Okay, so the theme of this talk is that I'm going to describe some novel asymptotic limit for massive particles in four-dimensional flat space. Now, the original motivation, as I'll explain in some detail, was to understand holography in flat space. So it was about, how do theories of gravity behave in flat space? That's why we started thinking about this. However, the formalism that I'm about to describe, and in fact, most of the talk that I'll give today will be about non-gravitational theories. So it's not about gravitational theories, even though the motivation comes from holography, which only makes sense for gravitation. Now, since, as you will see, I'm about to do something somewhat unusual. I'm going to describe some unusual limit for massive particles. A very natural question that some of you might have is why we are doing this. Why is it that we are spending all this effort describing this limit of massive particles at spatial infinity, which is not the natural home for massive particles. So I want to spend, maybe 5 minutes trying to explain what the motivation for this is. Why is it that we are undertaking this exercise. So for this purpose, I'm now going to review some older work going back a few years, which some of you are probably familiar with, but maybe not all of you. And the purpose of reviewing this older work is simply to explain, why we're going to take this, describe this analysis of massive particles.
So just to understand terminology, the natural place for a massive particle is time.
Future infinity and past infinity. Exactly. This is something I have to do? Okay, so the motivation for this comes from this general program that several of us have worked on and applies in several different settings, which we call the holography of information, which is the slogan that goes along with this is that if you think of a theory of quantum gravity and you think of observables in the complement of a bounded region, then if you know all observables in the complement of a bounded region, they also fix observables in the region. In the simplest case, where you can think about this, think of a Cauchy slice in flat space, and then the claim would be that if you know everything out at infinity, if you have an observer out at infinity who can measure all kinds of observables out at infinity, maybe very complicated observables, then they also have access to information that you might naively think of as living in the bulk. Of course, in the case of ADS, we are familiar with this because this is what ADS-CFT tells us. It tells us, if you go to the boundary of ADS and you make all sorts of measurements, then you might have thought, in a non-gravitational theory, you would be right, that there is some data in the middle of ADS that, commutes with all the observations you make at infinity. But in a theory of gravity, we know that's not the case. And in fact, the degrees of freedom at infinity also capture what is happening in the bulk. There is a version of the statement in flat space, which I'm now about to review. There's also an interesting story that one can tell in de Sitter space, which I won't have much to say about now. However, there is a version of the story in flat space that relates to the talk I'm about to give, and that I'll present now as motivation. Okay, so the version of the story in flat space is the following. Think this is a picture, it's slightly, unconventional way of drawing the Penrose diagram of flat space. But this thing on top is what you call scribe plus, which is future null infinity. And this cone at the bottom is scribe minus, which is past null infinity. Now, if you think of a non-gravitational theory, I'll say something for future null infinity. Everything I say for scribe plus is also true for scribe minus. And there's an analogous statement, but I'll just make the statements for scribe plus. Yes.
So you use the word information.
Yes.
But it's more than that. At least in ADS, it's more than that. You can actually create things.
Same thing. All observables. So if you fix all observables outside, you know all observables inside.
And you can act on the outside to create.
There's a relationship between observables. So observables outside are the same as observables inside, which is what I'm about to say. This is the statement here. So if you think of the asymptotic algebra and a non-gravitational theory at scribe plus, the way you parameterize scribe plus is by what's called the retarded time, which runs from minus infinity here at the past boundary of scribe plus to plus infinity on the top. And in a non-gravitational theory, you have independent degrees of freedom, or you have independent operators at different values of the retarded time. Okay, so if you look at the full algebra at scribe plus, that algebra at scribe plus comprises independent operators. There are some operators you can define at scribe plus, which are limits of bulk operators. I'll make this precise in the next slide. And you have these independent operators at different values of retarded time. What you can show is that in a theory of gravity, any operator in scribe plus can be approximated arbitrarily well by a set of operators near the past boundary of scribe plus, which are operators in this retarded time interval that goes from minus infinity to minus 1.
So really just digest that. So the difference is that it doesn't go from minus infinity to infinity, but just stops.
In the Penrose diagram, it looks like a small interval, although it's actually a semi-infinite interval.
Which gets
this red region here is actually this region minus infinity minus 1 over epsilon. Although it looks small in the Penrose diagram, it's actually semi-infinite. Okay. Let me now try and prove the statement for you. Let me give you a lightning review of the proof. And the reason I'm doing this is not because I want to discuss this story, but because it will tell you what is missing in the story and why the story of massive particles is relevant.
So you could have colored almost all the way up to the top also, right?
I could have colored all the way up to the top. I want to color as little as possible to make the statement as strong as possible.
But that's about coloring though.
It's about coloring, you're right. So in the end, the statement is, well, I don't know, why is it about, it's about the statement that you give me any, you give me any epsilon interval, you give me an interval that, any interval from minus infinity to some, why do you say, why do you say?
No, but there's no sense in which it's a small.
It's a semi-infinite interval, you're right. It's hard, so you could think of it as, the reason it's semi-infinite actually is for there are several reasons it's semi-infinite, you would see why it's semi-infinite. Maybe, one place a different setting where you could think of it would be ADS, where it's really generally a small interval. There's a boundary time and you can think of 0 to 1 over epsilon. Here, one reason why we need this semi-infinite interval has to do with how operators behave at scribe plus and why you need a semi-infinite interval in order to dampen fluctuations. But you're right, there's a semi-infinite.
Sorry, I'm confused. The coordinate on scribe plus goes from minus infinity to plus infinity, right? So you're taking about half the region.
Taking about half the region. Or it's epsilon, you can think of, you're taking about half the region.
Okay.
Although it looks small.
Yeah, it looks small.
You would like to say something stronger. You would like to say that
Is pick a finite. That doesn't work.
Finite thing away from minus infinity.
Yeah.
So that would miss information to its past. So if you picked a finite interval, say, there's several problems with it. One of them has to do with defining, observables in a finite cut, which in fact turns out to be remarkably subtle. But let's say you picked a cut at u equal to u0 and u0 plus 1 over epsilon. That cut would actually miss everything to the past of u. So that you can already see. So if you pick a cut at finite things, it's already missed half of space. Which whatever
you want to do an expansion of some function in some interval. For that, the finite interval is necessary. Insufficient.
That's right. Finite interval is sufficient.
More.
But the thing is that if you pick a cut at u0, you miss everything from minus infinity to u. So the moment you pick the finite cut, you've lost an infinite amount of information because the infinite amount of information flowed past you. Now you could say, let me restrict to a set of states so that all the interesting stuff happens after u0. And then you might be able to say you look at u0 and u0 plus epsilon. But there's some additional subtlety in having to define observables and like plus and multiple dimensions, which I don't want to go into. Yeah. So
Is it not like it's like time evaluation of state?
yeah, you can think of it that way. So indeed, you could think of it that way. However, there's something which is, you see, if I give you the same data in a non-gravitational theory, you would not be able to time evolve it because the Hamiltonian would be an integral over all of scribe plus. What's special about gravity, and in fact that's one way to think about this, is that the Hamiltonian lives here in the past boundary of scribe plus. So indeed, if you give me this data, I can evolve it in the future. I'm going to say that in slightly different way.
So I mean, that is the crux, just to understand that if you gave the data just in the red sliver, then given that and the Hamiltonian, is that right? Then you
Well, no, the Hamiltonian lives in that red sliver.
Is part of that.
Because it is the boundary.
Is part of that. Okay, thank you.
Okay, let me make this a little bit more precise. So, both gravitational and there were these operators y on the previous slide. What do those operators y mean? So, if you look
in ADS, we know more is true. You don't even need an interval.
Yeah.
It's one slice.
Yeah, yes.
Do you suspect something?
I suspect something like this should be true here. And in fact, if we applied the same arguments we have to ADS, the result we would come up with is that you give me a band on ADS from 0 to 1 over epsilon, 0 to epsilon. But we don't know how to squish it down to a, the reason roughly is that in this analysis, we don't see the large n. For that, you need the large n. You're kind of working with the glue ball degrees of freedom. And so you don't see the separation into n. So to really go down in one dimension, you need to have something, do something more than what we do. So we are not actually going down a dimension. It's not strictly holography. We're saying you can squeeze things, but we're not saying you can go down 1 dimension. That's also true in DC and everywhere else where we do this. Okay, so both gravity. So there were these operators y. So what was this operator algebra I was speaking of? Well, the way you define the operator algebra is by taking an extrapolate limit from the bulk. So think of gravitational fields. When you think of gravitational fields, the kind of fields we want to sum over the quantum gravity path integral, or the kinds of fields we want to consider, are setups where, to leading order, the state looks like it's asymptotically flat. So it's important we don't consider states which destroy the asymptotic flatness of the space. So the space is asymptotically flat. So to leading order, the metric is just the Minkowski metric, which is the thing you see on top. And then there are fluctuations which are suppressed by 1 over r. These fluctuations are called the shear and the Bondi mass. And these fluctuations are what you extrapolate to infinity to get some degrees of freedom at scribe plus. So you take this CAT or this MB and you think of these as defining some operators on scribe plus. You're familiar with this because, in fact, in a different language, these are also the operators you use to define the set of out states and the set of in states, okay, when you define the exercises. Similarly, if you had some other massless, for instance, a massless scalar field, it would have some limit at r tends to infinity, which would be a 1 over r limit, and then the coefficient of that would be an operator that would live on scribe plus. So, I want to make some statement about a theory of gravity. We don't know what the UV completion of 4-dimensional gravity is. But yes.
Just one question. If you were to draw this timeline process and take some finite time and then take a limit as they go to infinity, then that would, you always keep that time finite. Right? So then would you get around?
It would go to, that interval would probably go to I naught. Probably go to spatial infinity.
Yeah, so
you take this.
Would you be able to recover?
So I'll say that's what the talk will be. But in what I'm about to say, I really want to look at scribe plus. But then I'll say something more. I'm going to spend most of my talk talking about I naught.
I naught is this point.
Is this point. And that's what you're thinking of, right? You're thinking of an interval that goes. Maybe ask the question again in a few minutes, and then I can answer it. That's indeed what we. Although we talk about massive fields, but you could ask many things. We'll have to blow up I naught first of all. It can't be a finite interval, but let's just discuss it in a few minutes. Okay. So I want to define the operator algebra by just thinking of bulk operators and taking them off to infinity. Why is this a good thing to do? And this is a good thing to do because we believe even though we don't know the full UV complete theory of gravity, we think the asymptotic algebra continues to make sense in the full theory. You see, if I started talking about bulk operators, I said, there's a bulk gravitational degree of freedom. I don't know what that's going to do, in the UV complete theory. I don't know how to define it in a good way in the UV complete theory. But we still think that even in the full string theory, the S matrix makes sense Therefore, the asymptotic limit of these bulk operators makes sense. So the assumption is that in the full theory of gravity, whatever that is, this language of talking of asymptotic algebras is still a meaningful language. In ADS CFT, for instance, we would say that you talk of these asymptotic limits of bulk operators, and that gives you the boundary CFT algebra. And that's a meaningful way to describe the physics, even in the full theory. So we would hope that something similar should be true in flat space. And indeed, it's an assumption of this analysis that this asymptotic algebra makes sense. And then I want to define the algebra of all of square plus and the algebra of this interval of square plus, which comprises this retarded time from minus infinity to minus 1. Okay, that's so A epsilon means this red region, and A otherwise, when if you see it, is the full algebra. Okay. Now, the second assumption I'm going to need to give you this proof is that the Hamiltonian is bounded below. So if the Hamiltonian is bounded below, then you come up with the following statement. You think of the Hilbert space of the theory. Now, the Hilbert space of the theory, even in the full UV complete theory, you can get by doing asymptotic quantization. You can get by saying that if you go very far away, then whatever particles you are just become free particles. Therefore, you can talk of some set of free gravitons or free strings, and that's some simple Hilbert space. And the way you get that Hilbert space is by taking this algebra that I described, this asymptotic algebra, and by acting on the vacuum, which is the lowest state of the Hamiltonian. Now, another thing you get from the fact that the Hamiltonian is bounded below, that
this would not be exactly true in ADS.
This would be true in ADS.
Would not just be a Fock space.
It would, but I never assumed it's a Fock space. I'm not saying anything about the inner product. I'm just saying this is the span of all of these operators acting on the vacuum.
Okay.
That's all right.
But in this case, you expect really that the Hilbert space is this.
In flat space, you expect, but in EDS also you expect really the Hilbert space is this.
But you have all the relations because of trace identity.
You have relations between them, so the inner product is complicated. Here the inner product is trivial, but the inner product in ADS is complicated. The complicated inner product here is between scri plus and scri minus. In ADS, everything lives on I0. And indeed, when we see everything lives on the boundary, when we go to I0, we'll see again this complicated inner product appearing also spatially.
But just a minute about scri plus, so does this suggest that this theory, whatever it is, has no trace identities?
This theory is just the trivial out space. So this is a kinematic statement. No. So presumably the boundary theory, if you wanted to see some sign of dynamics, you would also have to say something about scri minus and scri plus. So here I'm saying something only about the algebra on scri plus. But whatever captures the dynamics would presumably also have to know something about the S matrix.
But just to push on that,
yes.
In ADS, single traces make a Fock space approximately until you get to energies of order n square. Then it becomes very bad. Here we expect this Fock space picture to be exactly correct always. That's right. So doesn't this suggest somehow that there are no trace identities in this Hilbert space?
It suggests there are no trace identities in the boundary theory.
Right, it's the trace identities that start making the Fock space bad in ADS.
Maybe. Maybe. Okay, I don't have anything to say. Maybe, yeah.
In ADS, you could have said that this is like a large algebra, right? And strictly.
Yeah, but this is really the algebra I want to work in. This is an exact thing.
Yeah, that's because the Hilbert space asymptotically is true.
Yeah. Okay, maybe then, maybe one way to say it is there are no trace identities. Yeah. Okay, I don't have anything to say about it.
It's non-gravitational, right?
This is the gravitational. It will also gravity. This would be true in string theory.
Maybe you get to the flat space case by taking n to go to infinity from the power.
It's actually, yeah, probably not. You get strictly flat space by taking n.
No. Strictly. Because I think you want to keep L. Yeah. So you want to keep. Yeah.
I don't know. I was thinking like the BFS limit.
Yeah, maybe.
I know it's
because you want to keep G string finite because you want string length to Planck length to be fixed. But you want to take lambda to infinity. So maybe you're right that you take lambda to infinity, so you take n goes to infinity, and maybe that's right. Yeah, maybe that's right. Maybe that's okay. But there's another interesting statement which might be somewhat surprising. So the top part is the Hilbert space, which is that any element of this Hilbert space, which you would have thought you would get by the action of the full algebra on scri plus in the vacuum, you can in fact get by the action of the small algebra on the vacuum. So
sorry, but about something,
that's right?
Because we get n, keep G fixed, take n to infinity, you get flat. So that's like it's strict n to infinity. So no doubt. Yeah.
Could be. That's it. Yeah, you have to keep G angles fixed, so it's not a Toff limit. You go beyond the Toff limit.
Beyond the Toff limit, but that's what gives you flat space, right? It gives you flat space at a fixed string coupling. So you take it, and strictly to infinity, so it's really the place identity of God.
Okay, yeah. Okay, so this is a statement about the Hilbert space. Now, the statement that is surprising is that any element of this Hilbert space you can also get by acting with a small algebra on the vacuum. This comes from the positivity of the Hamiltonian. Okay, I won't try and prove this, but this is some version of what's called the Richtlieder theorem. Okay? And it comes by just I won't try and prove it, but it's something you can prove without so much difficulty, and it really only assumes positivity of the Hamiltonian. It would be true also in a quantum field theory.
What is the statement?
The statement is you act with a small element of the small algebra.
Small algebra is
the algebra from minus infinity to minus epsilon. This is a epsilon or minus infinity epsilon. Let's just call it a epsilon on the board. And you act with an element of the small algebra on the vacuum. That gives you the same as acting with the big algebra on the vacuum.
And so I'm sorry, I don't know that very well, but certainly for usual Richtlieder that I have looked at, it's some space-like slice I had in mind, and as you say, the state is so entangled that even though you're acting here, you're actually able to.
Here also,
you know enough about the structure of this.
Yeah, because you just need positivity of the answer. You need the following thing. Imagine there was a state which you could not get. You look at this correlation function, and think of first states you get by the action of one of these y's. This correlation function is analytic when U is extended in the upper half. Upper half or lower half plane. When it's extended one side. It's because of the positivity. Because you can insert a complete set of energy eigenstates, which was my assumption. And because of that, if this correlator vanished for U in minus infinity to minus epsilon, it would vanish everywhere. And therefore, it can't vanish anywhere. Therefore, there can be no state that's orthogonal to all states generated by the small algebra. Therefore, there is no, this is the full inverse.
So this is also true for a finite band in U.
This statement would also be true for the finite band.
This Hamiltonian is the usual ADM Hamiltonian.
This Hamiltonian is the usual ADM Hamiltonian. Moves up and down. Because U is T minus R. U is just T minus R. The usual ADM Hamiltonian moves you up and down on square.
So for this statement, do you need you to start from minus infinity?
For this statement, we don't need you to start from minus. You could start from anywhere. Actually, you can generate it by anywhere. For this statement, you don't. For this statement, you do. However, this statement is also true in non-gravitational theory. The next statement is that, in a theory of gravity, the Hamiltonian itself is a part of the small algebra. And in particular, one of the bounded functions of the Hamiltonian is a projector onto the vacuum. And that is an element of the small algebra. This is a unique property of gravity. This is true only at U goes to minus infinity. It's the fact that if you measure the energy, and what quantum mechanics tells you, if you measure the energy, there's a probability of finding some answers. What's the probability of finding 0? That's given by the expectation value of this projector on the vacuum. And this is an element of the algebra. This is something that follows from gravitational constraints. And this is a unique property of the vacuum, of a gravitational theory. Would not be true in any other theory.
Oh, sorry. So I understand that this is an element of the algebra.
Yes.
And then what's the rest of the statement? That it lies in the, what's the rest of the
This is an element of the algebra. That's all I've made. That's all the statement I want to make here. And I want to say in the full UV complete theory of gravity, it will still remain an element of the algebra.
But what do you need gravity for?
For this would not be a boundary term in any other theory. This is an element of the algebra. It lives here, right, in the past boundary. So the EDM Hamiltonian lives here. And at U equal to minus infinity. In any other theory, the Hamiltonian has some integral.
So it's an element of the A epsilon.
Of the A epsilon. That's. Okay. If you accept all of these statements, then this is how the rest of the argument goes. Think of any element of the algebra, okay, on Scribe plus. You can expand it in the complete basis of states. That's just quantum mechanics. Now I can approximate any element here by an action of the small algebra on the vacuum. I'm calling it small algebra, but later turn out to be the full algebra. And then I can replace in a theory of gravity this middle element, which is bra 0, ket 0 by the projector on the vacuum. And now you see I just have a product of a sum of elements. I have a sum of a product of elements in the algebra. So this is also in the algebra. This tells you that any operator that maps the Hilbert space back to itself, you can get approximate arbitrarily well by an operator near Scribe plus. Okay, so this is the version of the statement. This is a proof, a very fast proof of the statement that I do. However,
What would it be approximated?
approximate arbitrarily well is because this state you actually get, you approximate arbitrarily well. What you really proved was that there was no state that was orthogonal to the set of all states you could produce. So you can get arbitrarily close. So really a statement is it's dense in the Hilbert space. So
That's used in step 2.
That's step 2, yeah.
There can be many such representations because I mean, you can write and get as extent acting on will taken
in many different ways. Yes, there could be other representations which would be said to be equal, because once you insert the P0, they would all be equal. They would all be very close to each other, depending on how well you approximated them in different ways.
Are these the relations?
These would be some relations, yeah. But these would be relations that come from entanglement of the vacuum. I don't know, they're not the same large n relations. They're the fact that the action of some operator in the vacuum is the same as the action of some other operator. That also happens. Okay, so now you can generalize the story. There are many things to say. As I said, this generalizes to ADS. You can play games like you can say, what if you really had some observers and they wanted to extract some information in perturbative states? This is not just a formal statement. And then you can play a game and set up protocols for these observers to detect what's happening in the middle. And that sounds surprising. You might have thought that maybe this is true in some abstract sense, but you can't really measure what's happening from infinity. But you can. It also generalizes to DS. And I think there it's interesting. And let me just point out why it's interesting. You see, the statement I made was, the slogan I gave you was, observables in the complement of a bounded region have all information about observables in the region. If you think of de Sitter space and think of how the Cauchy slices go, the Cauchy slices are compact. So any little region, any open set is the complement of a bounded region. Therefore, the claim there is that, if you look at cosmological correlators in any little region, they are sufficient to tell you correlators everywhere. I have to make the statement precise in many ways, which I don't want to do in this talk, but that's an interesting way in which the story generalizes to DS.
Sorry, what is the analog of the Hamiltonian statement here?
There is no analog of the Hamiltonian statement here. Roughly, the analog is that all states that you have to be invariant under. So the Hamiltonian here is 0. There's no boundary term. Unlike the case of flat space where there's a boundary term, here the statement is the Hamiltonian is 0. And so roughly, it's the statement that all states that you have to be conformally invariant. So you can have different states in the Hilbert space, but they all have to be conformally invariant. Therefore, if you give me the properties of the state in one little region, I know they might be. Yeah, exactly.
But this is also true probably for quantum field theory.
This is not true for quantum field theory. Quantum field theory, there's no constraint. You don't have to apply a Gauss law constraint. You have
that statement about the values of correlators being determined from values of correlators in a small field.
No, because
for a CFT.
In a CFT vacuum, but in a CFT there are other states which spontaneously break the conformity. So it's not true that.
Which CFT are we talking about? CFT inside de Sitter?
Here I'm just talking about states in de Sitter, wave functionals in de Sitter.
No, when you said CFT,
I meant, in any CFT, if you are in the vacuum or any other state that preserves.
This is true.
The
analog statement here is that the wave functionals in de Sitter have to preserve a version of conformal invariance, conformal group being the de Sitter group. And that tells you that if you give me how the wave function is behaving in one region, I know how it's behaving everywhere. There are many possible wave functions. You can set up some rich Hilbert space. But all of those states have the property. If you give me how they're behaving in one region, you know how they're behaving everywhere. This is not true in a CFT. In a CFT, if I give you a state psi, and I tell you all correlators, O of x1, O of xn, in some region, x1 in some region, you don't know how these states behave outside that region. If I told you the state psi was a vacuum, then of course you know how they behave. But if I don't tell you the state, I just tell you I'm in some state psi, I give you these correlation functions in some region, tell me what they are everywhere, you can't do that because the state psi might work conformally. But in this
analysis, you will not.
No, because states are not analytic. Right? Because you can have energies which are unbounded. This state could have some energy which is unbounded above. Which is not bounded above. So it's not analytic. So these correlators are not analytic. But in de Sitter, they are. In the presence of gravity in de Sitter space, and they are. But this is a separate story, yes.
No, I was just going to say that in CFT, you could have acted with any unitary in the complement field and got the difference.
Exactly. Yeah, because you have exact microcausality. Exactly. That's one way to do it. Exactly.
But by the way, I know your talk is not about de Sitter, but in de Sitter, if you had stuff inside, you would probably pretty similar.
No, but the stuff inside has to be such that it has to be conformally invariant. So you see, the constraints tell you that whatever stuff you put in, whatever allowed states there are in the Hilbert space, have to have this property of conformally invariant. So the constraints force you to look at only this set of states. Okay, this is also an interesting story for the black hole information paradox because, the paradox arises by assuming that the region outside has no information about the region inside. And if you take seriously the story that, the region inside, in fact, operators inside should be related to operators outside, then many paradoxes go away. And, so this is indeed something that's of interest also for thinking about black holes.
The time to the mechanism that is usually proposed for this?
Well, there are different mechanisms that are usually proposed for this, but generally, at least what I would say, one set of people, so this is true also in the island story and other stories, that operators inside are related to operators outside. That's certainly true in one set of things. There are some people who would not agree with that. For instance, Samir Masur would not agree with that. But the point is that this relationship between operators inside and outside, you see, is a feature of gravity. It's not something you're putting in by hand. It's not something. In fact, I think the island proposal actually obscures some of the fact that it's really a feature of gravity. So, those calculations are nice. They do something else for you. But this fact that it really arises from gravity, you don't have an option about this. And the fact that you also see this in low energy, and the fact that you can prove this starting with these assumptions, I think is one reason you should really believe it. It's not a feature of specific models or a non-gravitational path or something. So, okay, but that's just my view. But that's a sentence. So all these are sentences.
But Alan, people seem to require a non-gravitational.
Yes, they seem to require a non-gravitational path to get an island. That's right. So you in that case, you require, but you don't. This property, as I'm trying to say, is a general property of that. You don't see anything. In fact, in the island, there's something. Well, let's not get into that.
Okay.
Yeah. Yeah. Okay. Yeah.
Just one last thing. I know you want
Yeah.
These operators in the interior of the black hole, are they the same kind of operators that you might expect on A minus epsilon?
I think so, because in the end, you would have thought, if you went back to the story, that in the end, the black hole would evaporate away completely. So whatever operators you have in the interior would be some operators you would be able to write on Scri plus. And what this is saying is that those operators you would also be able to get before. Maybe another way to say it is this story. The statement is that you sit here on the boundary, you make some observations, you know what's happening inside. So this is a statement that, what is this black hole paradox arises from the idea that information has gone inside, and it's really gone inside. It's not available outside. But, if you recognize that information can't really go inside, that there's always some trace that remains outside, then you would not have set up these, that would resolve a lot of these paradoxes. But that's some separate story. Okay, what I want to talk about today is the fact, yes.
It seems too quick disposing of the information puzzle. Just because black holes evaporate all the information.
No.
Plus,
I did say that. I want to say
on a Cauchy slice, you have an operator inside which can also be represented by an operator inside.
But
on that Cauchy slice, that seems a much more non-trivial.
But that was the statement that I was making previously, right? Because you see,
so you should go on and explain it.
No, but it is the fact that you take an operator here, you can write it as an operator here. This you would probably agree with. Now I've told you that all operators here you could write as operators here. Therefore, you can write an operator here as an operator here. So that was but you can also do it more concretely. As I said, if you work in perturbation theory, you can explicitly show how you can read off information here in terms of something here. And that gives you some, if for the black hole, you knew how to write the operator here in terms of the operator here, I would give you a formula of how to write it in terms of the operator.
Well, I think the statement of complementarity, which is the older version of Island, but Island just implements it, is that the same operator is represented.
Exactly what I'm saying. Yeah.
I think it's a little different from here.
No.
On a space like slice, isn't it a little different? On a space like slice, at least physically it seems, I can do something outside and create a truck deep inside. A massive violation of locality. That seems a little different.
No, exactly what I said. When I was saying that the full algebra on Scri class, you could write as something here. That means an operator here, which you would have represented, which is in the middle of the Cauchy slice, I'll actually write in terms of an operator here.
But what if there's singularity?
If there is,
that operator
Is it
there
singular?
but this, in the end, all black holes evaporate. The singularity
I don't know,
goes
in
away.
terms
This
of
is spectral
space-
diagram.
on a space like slice, does it mean some operator very far away on the space like
Yeah,
slice?
because an operator, that's an operator far away on Scri plus.
He's saying you can write every operator in the whole space time.
All operators on Scri plus, actually. I haven't said something about I plus, but all operators on Scri plus. So if you just stick to mass
And
plus,
then-
yeah.
Then it will
then
protect it
back.
back. There's some infinities involved, but I guess you take Scri plus as some limit. I give so-
You take Scri plus at some limit. You could do this in ADS if you don't like Scri plus. Maybe it's a cleaner example. You put an infrared.
And will it necessarily not have support on the timeline?
But the time lag infinity is what I want to talk about. That's a question of massive particles. So, usually for black, let me say something about, I won't do it. Let me get to time lag infinity. Yeah. Okay, good. Now, there's something I missed in this whole thing, which was, in this discussion, we kept talking about Scri plus, but as Abhijit said, we missed the issue of I plus and I minus. So what lives at I plus and I minus? Well, massive particles live at I plus and I minus. If you think of massive fields, they do not have a good limit to Scri plus. So you cannot extrapolate massive fields to the algebra on Scri plus. So what I said was, the full algebra on Scri plus you can write near its fast boundary, but the full algebra on Scri plus does not include extrapolated massive fields. It includes traces of massive fields. If you have a massive field, the massive field has to come with a gravitational field. You can detect the gravitational field of the massive field, but you can't detect the massive field itself. Okay, now there is actually a perfectly good description of massive fields at time like infinity, in the far future and the far past. Now, usually when we teach quantum field theory, we don't emphasize this. But in fact, if you were to think carefully of what you're doing in the LSZ formula, you're actually extrapolating massless fields to Scri plus, and you're extrapolating massive fields to I plus, and I minus and Scri minus.
Moving along how they move.
That's it, exactly. So this is the geodesic of a massive particle goes from I minus to I plus.
So, is it correct that if you want to explain away this information paradox, you would then have to show that the information at I plus is also somehow already outside?
You could, for the information paradox for black holes, what people usually say, by the way, in the islet story also there are no massive particles because it's always massless particles.
For example.
No, so usually, so let me say. So usually for the information paradox, what you say is you take a black hole which is big enough that almost all its radiation comes out in massless particles. Therefore, you don't have to worry about what happens in atoms. When people say there's a P, when you want, so, and that's also true, by the way, in the island story, when people have taken conformally coupled, have taken a CFT in the bulk, which is coupled to a CFT outside, so there are no massive fields. So, in fact, in a lot of this, you're anticipating what I'm about to say, but in a lot of discussion of black holes, massive particles have basically been ignored by saying you take a big enough black hole, and it basically doesn't radiate any massive particles. So, you just forget it. So, that's one reason I think this issue has, might not be so relevant for the information paradox, but I think it's relevant.
Work in a universe with no mass.
Yeah, you could work in a universe that has no massive particles. That's right.
Pure.
Yeah, pure. But okay, so you could say that that's one option. So there are several options. You could work in a universe which has no massive particles, as Shreya said. That's option 0. Massive particles don't exist. There are no massive particles. Or you could say that we declare all observables in the theory are available on Scri plus minus and I plus and Scri minus plus, which is here, and I minus. Okay, so either you look at this and I plus, or you look at Scri minus, squeeze it to Scri minus plus, and look at I minus. That's fine, and that's probably a true statement. If you give me the algebra, which was the algebra here and the algebra of operators here, that would be fine, but it's not kind of in keeping with the spirit of holography, which is that information is available at the boundary of a Cauchy slice. So I plus is not quite the boundary of a Cauchy slice. Okay, so this is probably true, and maybe it's even an interesting statement. Maybe this is the correct way to go, I should say, but I'm not going to say much more about this because this is not, it would be nice to find some way to represent things at the boundaries of Cauchy slices. Okay, the second thing is you could say, well, don't worry so much about the fact that massive particles don't extrapolate to Scri plus, just work at large R. And then, work at large R, and then you can talk about massive particles. This is something that I think you also said. But, it was pretty important that in what I was saying, that I wanted to work at asymptotic infinity. The reason it was important was because the bulk fluctuates in a theory of gravity. So if you start talking of observables at finite R, then you have to answer all sorts of questions about how you define those observables at finite gravitational coupling. And therefore, I really want to speak of observables at infinity. So that's a drawback of this option. Option 3, this is in fact the option we already discussed, which is you forget about massive particles. And this is not facetious completely because for some questions about black hole evaporation, they probably don't matter. However, this leaves us with some incomplete picture of how you represent all states or where all states should live, where all the algebra should live. So for this purpose, I'm now going to describe this novel limit of massive particles at I0, and that was a rather long-minded motivation. But the point of this was to tell you that what I'm now about to say is an interesting problem because Scri plus is not a natural home for massive particles, and Scri plus and I plus is not a natural home for holography. So you might want to look for some place where you can write down massive fields, maybe also massless fields, and maybe that place is I0, which is spatial infinity. Okay.
You just made comment that the effect of massive particle can be obtained on Scri plus, right?
Yes.
So then we have
we have some, but now people maybe there are no global symmetries in gravity. But for instance, imagine there were two massive particles, there were two fields which were related by a global symmetry. If there were, then you would not be able to distinguish between them just using their gravitational field. So the fact that you can tell the gravitational field, it's not clear that you can actually you can reconstruct all massive operators from the gravitational field. Maybe you can, but it's not clear that you can. Okay.
Sorry, this is probably very irritating question, but let me just ask.
Yeah.
If I wanted to act on the state in asymptotically flat space with a projector onto the vacuum,
Yes.
Is this something that can actually be done?
Well, you'd have to measure the energy. So you'd have to couple the system. So the way you have to think of it is that you have a bubble of flat space, and you have some observers here who are measuring the energy. So they have some detectors which couple to the metric. And if they were to measure the energy, then indeed they would act, and they would not, you don't have to act with the projector, but by measuring the energy, if they measure the probability of getting 0, that would be the expectation value of the projector.
Nice. And the fact
acting with a projector is not possible, that's a non-unitary operation, but yeah.
I was thinking that it feels a little bit like you're saying these observers out of the system.
Yes, that's true. That the observers have to be kind of out of the system. In fact, if you're in the system, you probably can't measure the energy. So that there's this analysis by Caron-Huot and Bohm and so on, who try and ask, it's important to make all these measurements if the observers have to have an autonomous clock, which is not part of the system. That's how to be able to measure the energy accurately. So the way you would implement, at least the way I always think of implementing this is that you have some bubble of flat space, you have some observers, and they're kind of separate from the system. If you try to ask, what can the observers see if they're themselves part of the system, it gets very confusing.
So in some sense, you have an external non-gravitational sector.
You can think of it as an external non-gravitational sector, although we don't want to say anything about the details of that sector. We kind of want to say that, there's some operator algebra without saying something about the details. But yeah, we do have to have an external sector. Maybe it's nicer to ask questions about what observers can say from inside, and that's probably deep, but it's very confusing because there are many things that get, in quantum mechanics, we don't ask these questions. What can an observer say from inside the system? And then it gets very confusing.
Anyway, you should go on, but if one is really discussing the information puzzle, then one would like to know how hard is it to decode the information you claim is already residing.
You would get some estimate of that from here.
Something like this would be needed for that.
You would get
Because you need your projector acting, right, as part of the algebra.
So you would get some estimate of that by using these kinds of formulas. How hard it is.
And it should be sufficiently complicated.
It will be very complicated. Sure. Yeah. Okay, good. Let me now describe a different limit for massive
Just one last thing. It sounds like a really weird operator because it sucks all the energy out of the system.
That's right. It's something which that's right. But we know
it has to be non-local.
Such operators have to exist, right? Because such operators exist even from ADS-CFT. Forget about what I said. There's something you can do at infinity which tells you, and it's very counterintuitive. That's true.
Yeah, of course it exists.
Yeah. So you just measure the energy. If you measure the energy and you find, that itself will destroy everything if you really were to measure the energy in a coordinated. So
the energy, the big energy could destroy things locally, not so much.
If it's a big energy, but if the,
Vacuum is special, right? It's one.
The vacuum is special, that's right. But if you were to measure the energy and you were to find the vacuum, then you know that
Then
you
you
divide it.
that's the ultimate atom.
Okay, now you should go on that. I mean, the system has some energy, right? Let's say you form a black hole and so, right? It's in a non-zero energy state.
It could be a superposition of energy states. So maybe it's a superposition of,
No, but let's say it's a good classical state, right?
Then it's some,
built around some energy with a very small. Now, would you be able to actually implement?
I'm not trying to measure the projector on the vacuum actually. My formula looked like xn, p0, xn. This was just an element. I was not actually trying to measure p0. The formula actually looked like something like this. So I wanted to say any operator that acts here, I could write in this. Indeed, one of those elements is active, but I never wanted to act with p0. I was just saying p0 is an element of the algebra. Like, okay, it was.
It's the P0 that makes these oscillators very
It's the P0, but also the Xn actually. The fact that these this Xn is utilizing some properties of the vacuum. And if you wanted to create some state which was naturally created by the action of some operator here from here, that's also pretty good.
No, I guess for instance, ADS here is the HKLL operator, right? Those are very, in some sense, simple operators.
You'd write the same formula there, and you'd end up with the same issue that there are two sources of complication. One of them is, there's some operator which HKLL usually uses the time band of length pi. There's some states you write the same formula, and there are two sources of complication. There are some states which you naturally create acting with an operator here. I want to say you can create them acting with an operator here. That's a QFT thing, but I'm already utilizing some properties of entanglement of the vacuum. That's hard. And then there's also this P0, which is also hard.
Right, but that is not so hard, right? That is just time evolution of order 1.
Okay.
So I just to understand this P0, that is
the P0 is certainly the place where the gravity is coming in. Yes, but in the case of the black hole, that might be pretty hard because you have to evolve things which might come out after the evaporation of the black hole.
That's still order n, not exponential.
Well,
I mean, okay.
It's a question of how accurately you want to get the state, but yeah. Okay, but this is all tangent to the thing.
Fortunately,
okay, good. Now, so I want to describe something different, which is I want to describe a representation of massive particles on an asymptotic de Sitter slice, which is at infinite proper distance from a given origin. This, for those of you who are familiar with the literature and general relativity, is similar to what the relativists call the blow-up of spatial infinity. However, as I'll explain in a minute, what I'm about to do is slightly different from what the relativists call the blow-up of spatial.
Sure, this has nothing to do with the celestial sphere.
No, it doesn't, because the celestial sphere actually doesn't live anywhere. When people talk about celestial holography, they are not clear of where the celestial sphere is living. As at least it's not clear to me where the celestial sphere lives.
It's not I'm not sure.
It's certainly not a diamond.
No, it doesn't.
It's all over.
It's all over Scrapler. The celestial sphere, what they're really doing is
I see.
they take an S matrix and they Mellin transform it.
Given slides, right?
No, they just Mellin transform the full S matrix. They take the S matrix, but then that is, it's not clear. You can do that in non-gravitational theory also. You're just writing the S matrix in different variables. So it's not clear to me where that celestial sphere is. There are some words that go with this Dibor and Soludukin's paper, which is the celestial sphere lives in the middle of I of Scri plus and the middle of Scri minus. Something like that. But that doesn't quite play into this celestial world. Okay, good. So anyway, I'm going to talk of I naught. Maybe the celestial sphere lives at I naught actually. That would be nice. It would be a nice story if the celestial sphere were to live at I naught. And maybe it does. Okay, however, everything I'm about to say so far is now a quantum field theory talk. Which doesn't have anything to do with what I said about holography. So if you didn't agree with me or you didn't like what I said or if you were sleeping in this time, it doesn't matter. Because now I'm just going to say something which is QFT 101 discussion. Okay, so it's a very simple talk just about non-gravitational quantum. Okay, good. Let me say something about coordinate system. So I think this is Minkowski. So now, by the way, in what I was saying so far, I was talking about asymptotically flat space, right? So even though I'll still make a big deal of going to asymptotic infinity because eventually, as I said, the idea is to apply this to holography, everything I'm now about to say for till the absolute end is really just about really flat space. Okay, so I'm really in flat space, Minkowski space. Okay, so I'm doing quantum field theory in 4-dimensional Minkowski space. So nothing mysterious. So take Minkowski space and let's write it in these coordinates where this rho is just the distance, the proper distance from some origin that we have chosen. Okay, so we are going to break translation. If you write the metric of Minkowski space, it looks like this. It looks like d rho square plus rho square into minus d tau square plus cos square d omega square. And this is just a copy of de Sitter 3. These are the slices of de Sitter 3, these dash lines. Okay, these are de Sitter 3 slices. I want to focus on this is what I just said. Every constant row slice, if you focus on a slice of constant row, it's a copy of DS3. It will be convenient and you will see many times in this talk. And if you see our paper when it appears next week, we'll have these coordinates x. X is just a coordinate in de Sitter 3. So I might write a point as small x, which is the 4-dimensional coordinates, Minkowski coordinates, or in terms of rho, which is the distance, and this capital X. Okay, so we see capital X. Yeah.
These de Sitters are these black things.
The black things. That's it. Exactly.
And then on top, you could slice into.
You could slice into EDS.
Euclidean.
EDS.
Euclidean.
Yeah.
What is X?
X is just a de Sitter coordinate. It's this.
On a given de Sitter,
On a given
paper by row, right?
There are different de Sitters at every value of rho. So X is just the coordinate on the de Sitter. So to specify coordinates fully, I need to give you rho and X.
I see.
X is an embedding coordinate. X squared is equal to. Okay.
Sorry, X was the coordinate. I thought it's an alternate.
No, rho and X are the alternate coordinates. X is just the coordinate on de Sitter. X squared is equal to 1.
Oh.
Yes, X squared is just equal to 1. Sorry. Okay. Now let's take rho to infinity. And then, the boundary. So if you take rho to infinity, then you get a de Sitter 3, which is at the boundary. And this we'll call the blowup of spatial infinity. So you'll see the symbol I0 hat appearing, and that is the blowup of spatial infinity that I want to talk about. Now I said at the beginning, this is different from the geometric construction that the relativists use, which is the blowup of spatial infinity. So if I were to say this to Agar Sekar, he would get extremely annoyed. And the reason is that when relativists talk about blowup of spatial infinity, what they want to talk about is something slightly different. They want to say, focus on a region of constant tau, okay, compact tau support, and then take rho to infinity. If you do that, see what happens to these slices. You focus on constant tau interval and then take rho to infinity. Then these slices really go off and start going close to I0. Okay. What I will do sometimes is take tau to infinity while also taking rho to infinity. Therefore, you should think of the DS3 I'm talking about as this DS3 that really interpolates between square plus to square. So that's slightly different from the relativistic construction. But it's a DS3 that kind of lives at infinity, but it's like the blowup of spatial infinity.
So what relativists talk about is the left.
Is on the left hand side.
These tau slices.
No. For me, so far I haven't said anything different because I will sometimes also take tau to infinity. I'll say where. It's really appropriate for you to think in terms of this. That's right. Because if I was to go to a finite coordinate in tau, then I would really end up with what the relativists are talking. But you'll see at some point I'll also take tau to infinity. I'll tell you when it's important. Okay. So now let me say something about free fields in Minkowski space. So think of a free field in Minkowski space, which because I was taught at Harvard, we use the wrong sign convention. Coleman used to teach us. He didn't teach us the course. But okay, never mind. At some point we fix it to the right convention. I'm completely confused in my head right now which convention we use with the right conventions. This is a Klein-Gordon field. Satisfies something with positive mass squared. Okay, and think of how you solve so you can write down solutions to this equation. There's an unusual basis in which you write down solutions, and you can write down solutions in terms of the modified Bessel function. Okay, modified Bessel function of this rho coordinate multiplied with some field that solves the Klein-Gordon equation in de Sitter space, but has a de Sitter mass parameter, which is given by this nu. Okay? And this nu really runs from 0 to infinity. So all of these de Sitter are in the all of these de Sitter fields and the principal components. Okay, good. So now you can quantize these de Sitter fields. If you quantize them,
What could I see that one more thing?
I'm just writing 5 rho x as
Phi mu was what again?
Phi mu satisfies the de Sitter Klein-Gordon equation.
And the nu was the radius of it.
No, the nu is just a parameter I'm integrating.
But it satisfies de Sitter Klein-Gordon equation with where de Sitter. Oh, it's a mass. It's a mass.
Mass.
Okay, so
This new real new.
it's like radial momentum.
Real new is
Real principle.
So nu is like a momentum in the radial direction.
You can think of nu as being.
So it's like Kaluza-Klein reduced and therefore it's mass.
Okay, good. Now, you can quantize these fields, and if you quantize these fields, the Minkowski vacuum turns out to be the Euclidean vacuum in de Sitter space. In de Sitter space, sometimes we choose different kinds.
Assuming that mass is
No, this is just a Minkowski. You see, in de Sitter space, we can talk of different values of mass parameter. Here, I'm really just taking a Minkowski field and I'm breaking it up. This is the right decomposition of Minkowski field. The Minkowski field, if you break it up, doesn't have any other representation. It has all these principles. Okay. Now, when you similarly for the vacuum, in de Sitter, you can sometimes choose different vacuum. Maybe some people say I like to think of the alpha vacuum or something. There's no discussion here because the Minkowski vacuum is the Euclidean vacuum for these de Sitter fields. So the Minkowski vacuum is the de Sitter vacuum, and so you get some modes which are Euclidean modes in de Sitter space, if you quantize these fields. Okay, and then you can generate the Hilbert space. The Hilbert space is just generated here.
from the point of de Sitter, it is
It's an infinite series of massive fields. It's a Bunch-Davies vacuum. I like to call it the Euclidean vacuum because I'm thinking of global de Sitter. But yeah, you can think of it as the Bunch-Davies vacuum if you think of a Poincare space. Okay, so this Hilbert space.
So it has to be done separately on the right and the left.
Which is left or right?
I mean the
No. My picture here was just to say that the de Sitter is coming by. Actually, I should have brought. It's coming. I was just trying to show the Euclidean continuation of de Sitter to a sphere. That's what my cartoon was showing. This, you mean this and this? No.
Circle around.
Oh, okay, I see.
What circles are?
He was thinking there was a left and a right.
Yes, like
And there's no left and right. No. Oh, no. There's no left and right.
that is
The only one.
But actually, I must say, so that picture you showed where you had the de Sitter slicing.
Yeah, that was two-dimensional. Of course, it is circular.
It was but basically for every row I choose some dashed lines. Is that right? And then I just circle around.
Yeah,
that's correct.
And there's no left and right. That's only in 2 dimensions. In higher dimensions, no left. Okay, good. So you quantize this, and so anyway, so you can do this quantization, you'll get a nice Hilbert space. Now notice the following fact, okay? Notice at large rho, if you go to large rho, these Bessel functions, they die off exponentially, and they die off exponentially in a manner that is independent of this new parameter. So the Bessel functions just die off exponentially, and they all die off with an e to the minus m rho times the power law factor of rho. But they all die off as e to the minus m rho. Therefore, the proposal is, and I'll have to define this proposal, is you take the exponential tail of this field, scale it up with e to the m rho, and this operator is a boundary operator on the boundary GS field. So the proposal is you take the field, take rho to infinity, and pull out its exponential tail as you do so, and this gives you a boundary operator. Okay. So this is the zeroth order. Actually, this is the correct proposal, but I'll have to refine it. I'll have to say many more things about it.
This gives you the boundary analog of a field
on de Sitter 3. So this is now a field on this I naught hat, and this is a boundary field. So I want to say this is really a boundary operator. It's intrinsic to the boundary. There was a bulk operator, but now this is the boundary. So I want to go up to infinity and take this.
And just so I understand, you are taking rho to infinity, keeping all coordinates on de Sitter 3 fixed.
6, yes.
But what if I want to represent an operator which is as you're taking the rho to infinity, it lives at rho by 2.
What do you mean?
That you need a different denominator.
What do you mean the operator lives at rho by 2? I mean, it's like saying that
it's kind of what you're doing is that you're assuming that that operator is itself not moving. But if I want to represent some other bulk operator, which is going towards infinity.
Okay, I want to define a limit of bulk operators, right? A particular limit of bulk operators. It's like how we define an operator in ADS. So you say, so you say you have an operator at a value of r, you scale it up with r to the delta, you take r to infinity.
No, but actually saying you're focusing on a finite region around the origin.
On a finite region around the origin.
These operators that you're doing
Yes.
will correspond to wave functions that are order 1 in a finite region around the origin.
Wave function that are order 1 in a finite region around the origin.
Your wave, the coefficients that, there's some wave function whose coefficient is an operator. Your expansion has these.
Yes.
These operators, these KR.
Yes, that's true. Sorry, but I'm missing the point. What is the point that you're making? You're saying what? Yeah.
Abhijit is saying that these operate, that if you want to try to make an operator order 1 distance away from the origin,
Yes.
you would strip off an e to the power minus n rho.
Yes.
You would add e to the power minus
Yes.
n. But if you were halfway to there,
Oh, that's what you want. Yeah. Good. We'll spend a lot of time worrying about this.
I'm sorry.
I think the point is that this e to the m rho, has to do with that. Yeah. So let's say you if you're already halfway to rho equal to infinity, halfway to the boundary,
Okay.
then the factor would only be e to the m rho by 2. It would not be e to the m rho. So indeed, you'll have to worry about this when we define correlation functions. This is indeed the such. It's a difference between power law follows and exponential follows, and it's why this algebra is very simple. So this is what we'll spend a lot of time on. Thank you. Yeah.
Sorry, all of you are very smart, but.
No. Let me go on one more slide, and maybe I can say. If I go on a few more slides, I can say the same point again. Because I'll spend a lot of time. It might become an issue.
But just in one sentence, you make an algebra of operators that is, that has a good limit in an order 1 separation from the origin.
I understand.
Not further.
Not further. I completely.
Not the distance that deals with the.
I get it. Yes. Good.
And since all points in space are equivalent, you may why.
Yeah, well, what about the other?
Yeah.
Okay, thank you. Got it. Thank you.
So one thing. I took the opportunity to share.
No, that's good. You didn't fall, since you are an old timer, you.
The speaker keeps when since when I was a student at Harvard, the trick if you're giving a talk was to get the senior people to start talking to each other. Then you could talk about working, right? So then it was okay, good. So this is the zero thought element. I'll come back to all these points. Okay, good. Now in terms of de Sitter fields, this slide, I'm soon going to. I'm not going to say much more about. I'll stop using this description. But just since I introduce these de Sitter fields, this operator, extrapolated operator, is really just the integral of all of these de Sitter fields, just the sum of all these de Sitter fields, because the Bessel function that was weighting them has gone. Okay, so you can write down some oscillator expansion. Notice something unusual, which will come back, and it's related to all these discussions we were having. If you think in this oscillator expansion, you will see that the coefficient of these oscillators grows exponentially with this de Sitter mass parameter. And this is going to come back to Higgs in a minute.
So you show that this is Z of X.
Z of X is always my boundary operator.
Got it. And what was your curly F mu L tau?
Curly F nu L was one of the modes. It was one of the solutions, one of the Euclidean mode in this with this nu, and L was an angular moment. Okay, good. Now this exponentially growing factor, in fact, causes divergences in boundary correlators. And in fact, if you just naively look at the 2-point function of this Z of X1, Z of X2, it's not well defined. This is now I can explain this point that Abhijit was making. The reason it's not well defined is, you see, I'm trying to define some operators here, right? But imagine I'm somewhere here and I'm trying to measure the 2-point function with here. This distance is typically not 2 rho. The distance between here and here might be 2 rho, but the distance between here and here might be less than 2 rho. It could also be more than 2 rho in some cases.
Top's view.
Top view would help.
Then you have a circle.
Yeah.
It's like a chordal distance as opposed to going from here to center.
This has to do, it's a chordal distance. So it also has to do with the fact that the metric is indefinite sign. It's not just a Euclidean metric. So you can gain by moving in time. So you can move in the past here from here, and in fact you can go in proper distance which is close to 0. So when you do that, this
in equal time also there is an issue.
In equal time also there's an issue. In equal time also there's an issue. But you can also win by moving in time. And if you do that, you see this renormalization I was doing was e to the m rho, but the e to the m rho doesn't work because we rescale both by e to the m rho, but the correlation function is not dying off as e to the minus twice m rho. It might be dying off faster or slower than e to the minus twice m rho. So in fact, you just try to compute this 2-point function and find it's not well defined. Yeah.
So the information about the mass of the field has gone away, right?
It went into the renormalization factor, this e to the m rho. It appeared again in something.
Boundary operator doesn't.
Huh? The boundary operator will know something about the mass also. I'll say something a little bit more again.
This is just to make it well defined. And because it's exponentially die off, you have to blow it up so that non-die.
So this 2-point function is not well defined. If you just try to evaluate the 2-point function, you'll find it doesn't make sense. What's the solution?
So this divergence between n theta is a different divergence.
Same divergence.
Why? Because you wanted this n theta will appear even in the 1 point.
So 1-point function, you don't worry so much. It's just an operator.
And
You
one
might get.
function also you just remove. You didn't remove this pi.
Well, so in 1-point functions, the 1-point function vacuum is 0. Maybe you want to ask about the 1-point matrix element.
Yeah.
Yeah. If I looked at the right set of states, which were, as I'll say now, which had, which didn't have content, which had, say, bounded supported nu, then this would not give me a problem. But when you look at the state which is zx1, zx2, then one way to understand the divergence is this. The other way to understand it is the z of x1 acting on 0 creates states which are unbounded in nu, which are unbounded in the new parameter. And so, then this n tilde comes to kill you. Okay, so what is the solution? Well, here's the free field theory solution, which is you smear the operator. You can think of this maybe as focusing. Okay, so what you do is you take the operator z of x and you smear it with a smearing function g of x. What is the property this g of x has? It has the property that you can break up this g of x also in terms of these de Sitter modes. That so it's like a Fourier transform. So this g nu, which is like the Fourier transform of g of x in terms of these de Sitter modes, dies off exponentially as a function of nu. This function is de Sitter mass value. If you smear z with this function g, which has this property, then you get a smeared operator z of g, which looks like this oscillator b nu l times g nu l, where g nu l is this Fourier component. If you make this g nu l die off as fast as this nu, grows, then you will get a 2-point function, which is very different. Okay. So another way to think of it is these fields or these correlation functions are distributions on a particular class of smearing functions. You have to integrate them against particular classes of smearing functions for them to make sense.
No, but physically, just to go back to the point, does that mean you're restricting yourself to order 1?
It means you're focusing
to beam, a beam that will only intersect or order 1.
Yeah, or you focus it. Yeah, so you don't allow. You focus it. Yeah, you integrate over all something. So you focus in these distances always.
And then if you were to go back on a space like slice, that's some region of order.
So then you only be able to intersect at the center. This guy's focused here. This guy's focused here. So it will go like that.
So some region of order 1, say, and then you can do it.
Okay. Good. Now here's another way to say this. This language of G nu and all is very confusing. So in fact, now for most of the rest of the talk, I won't use this language, even though that was the easiest way to introduce it. Here's another way to say it. If you think of what this function z of g is, and you break it up, you just think of z of t, you think of various spherical harmonics for g, and think of g as a function of tau, where tau is the global de Sitter time. Then this is the statement that this function g is analytic in this strip, which is when tau is extended in the imaginary plane from minus pi by 2 to plus pi by 2. So when the global de Sitter time is extended from minus pi by 2 to plus pi by 2, this function gl tau is analytic. If you integrate this function z of x with these analytic functions, then you get something which has a well-defined 2-point function. By the way, there's something similar that happens in ADS-CFT in a different context, which has to do with the fact that if you think of smearing functions in ADS, this HKLL reconstruction in a finite temperature, but not about the vacuum. In fact, the smearing function is ill-defined. It is only well-defined if you think of it as a distribution that acts on correlation functions that have certain analyticity properties, which in fact thermal correlators do. So it's a similar thing, similar mathematical.
So it is different from the usual UV divergences because this high mu is just high momentum in the
it's usually for 2-point functions, if you separate the points, you don't have UV divergences. So here is something which is different that's happening. It's not really unique. Yeah, this is free. Forget about tree level. This is free theory problem.
So, I mean, if you have, let's say, the local correlators, their behavior with respect to rho would be this caudal distance.
That's right.
E to the minus m, this caudal distance, which is, let's say, smaller than this 2 rho.
Or could be larger also, but yeah.
Let's say in this case, it's smaller than 2 rho.
Yes.
Okay.
Yes.
And so in general, it would be infinity.
In general, the answer would be yes, it would be infinity or 0, but yes, infinity. Yes. In the case.
Now, when you do this smearing,
Yes.
I was thinking that smearing is picking out, getting support only from those configurations where the distance is 2m.
Exactly.
But there are also these configurations where it is more, so it would be infinity. I mean, if the smearing were the case that it's always less, then it would pick up contribution only from diagonal.
No, but the smearing could also exclude everything where it's infinity, right?
How does it exclude?
Well, I mean, I don't know how to say it quite in the smearing. Yeah.
But just in terms of there is a positive, negative.
Yeah, the smearing function roughly gives you a delta function for the correlator where it picks out points which are 2 rows separate. So I don't know how to say it.
You're just making a way back that exponentially dies off away from your beam.
Okay.
Just that.
But you take Z, the expectation value of Z square on
Z squared. No, I never want to take Z squared. I want to take Z of, you could take Z of G squared. You want to take Z of G? Yeah.
Is it not like 2 operators which are overlapping on?
No, it's Z of x1, G of x1. It's a smeared operator. So you first smear and then take the expectation values, and you'll get a good answer.
So basically, the point is that you're trying to sense exponentially small tails instead of power laws.
Yes.
That means you have to enhance them so much.
That's it. That's right. Okay, here's the 2-point function. In fact, this is the explicit value for the 2-point function. Remember, I said the functions for analytic. This is the explicit form of the 2-point function. This is an integral over de Sitter time, and I have to integrate over all global de Sitter time. I have to sum out spherical harmonics. That's kind of trivial. I extend one function, the function to the left to plus I by 2, the function to the right to minus I by 2. Notice here, by the way, you already see a difference between left and right. This is because I'm really considering Weitman functions. I've picked an ordering. Okay, so left is different from right. Okay? And so this is the answer for the 2-point function. This is the explicit answer. In fact, this is all there is to say about the free theory, because in the free theory there are only 2-point functions. Once I've told you this clear explicit answer for the 2-point function, so you give me a smearing function, I'll just calculate it. It's a very simple answer. That's the answer.
So just to relate to the previous motivational discussion, we have given up on the holography.
Right? We have not given up. We're talking about something else. We will come back on it. Yes.
We
are not talking about this.
To construct only those focus.
This is all non-gravitation. Okay. So indeed, for now we have given up on this. For now we are only talking about non-gravitational waves. So this whole discussion, in fact, is free field. So you're absolutely right. I gave a motivation. You could have said, I'll say something to justify my motivation. I'll say something in the end about a hope. But indeed, what I'm saying is
minus m rho tails would be there also in the gravitation.
Yeah, they will also be there in the gravitation. So I will say a little bit about how I hope this applies to holography information. But what I'm saying from now until almost the end is just non-gravitational theories and really flat space. Okay, so it's because this is all so I'm trying to make progress towards something. Yes.
Why did you have to choose left and right? Choose different scaling functions for left and
You
right?
could choose the same. You could choose the same one.
You said something about the get Weitman function.
No, I just wanted to say that Z of F, Z of G is not the same as Z of G, Z of F. Because F is extended, Z, phi of x1, phi of x2 is not the same. No, they're not spatially because they integrated. They integrated, so these configurations go through all sorts of different things. So they don't commute. So which one you put to the left matters, which one you put to the right. You could take them to be the same.
So just to go back to Abhijit's point, you're missing most of the operators.
What do you mean by most of the operators in this?
Everything that does not intersect the beam. So it's or more than order 1 away.
I think we'll end up reconstructing all the operators in this case formally. But why would you miss everything?
Because you're missing.
But in the end, you've taken infinity, right? You've gone off to infinity. But most harm.
Yeah, you've gone off to infinity, but it's a small fraction of your of the IR cutoff. So let's say the number of operators is proportional to the IR cutoff. You're focusing on a small fraction.
There's more length between
In fact, that's the point, right, of this focusing, that you focus on a.
Yeah, but maybe I'm missing this thing of why you're saying that.
See, the operators you're able to reconstruct are those which are order one distance from the origin.
Order one distance from the origin. That's correct. Yes.
Right. Now, suppose I take.
In that, yes.
Now, suppose I take some R. Maybe you can. Suppose I take some R and I take order one to be 1,000,000 and I take R to be 1,000,000,000. Then later I'll take R value to be infinity.
Yeah.
So I'm missing most of it. Right? It's only this part, but there's much more.
Okay, but you could alter.
And they're all finite energy. They're all the same energy. All these.
What do you mean the same energy with respect to the? But I could always say let me focus on some set of states. Well, let me say all the interesting thing is happening in some region. And then I'll focus on that, and then I'll take my thing up to infinity.
Right,
I'll go far away.
So you will have to do then a whole set of these focusings to get the whole all operators. Because you'll have to focus here and then there and then there and then there. And if you want to cover the whole space.
I'm not quite sure where this enters in the formal thing after you've taken R to infinity. Because after you've taken R to infinity, the scale is gone, right? It's not like there's a scale in the theory that's telling you what remains. So I mean, you're probably right in some sense that when we took. There were other operators we could have scaled with rho.
Yeah.
But let's say I took rho to infinity first, then in the end I'll have some description that's not clear where that remains. Like I say, maybe there's some subtlety in the theory that will tell you that I missed something.
You can see that there is one point, which is the point that you're covering, but there are so many points there, right? Conformal.
No, so what you're saying is that we are here and there's actually an infinite volume here. This is the infinite volume.
That's the origin.
This is the origin.
I think that is the only point that works. If you take a little bit away, well.
No. You see, once I go to infinity, unless I scale some operator as a factor of rho.
Yes.
So unless I'm very close to this point and I'm scaling my operator, so with rho as I'm going to infinity, I won't miss it. So let's say I decide once and for all that all the interesting stuff is happening in 100 light years. Then I take my limit, I'll get all that stuff.
Infinity is subtle. But suppose we have R, which is as big as you want. Then you've missed a lot. And then you want to keep things that operators that are not suppressed by some power of R or some exponential in R.
Yeah.
Then you've missed a lot.
So if you keep R which is big enough, then you've missed most of R. That's probably true in many of these discussions. That you sit there. Probably also true in
Any other point of the
No, I think what we are saying is you keep R finite, then there's a lot of space which is close to R. But what I would say is you decide to focus on a state or on a black hole or whatever, which was some size, and then you take R to be much larger. But most of the interesting stuff is not happening outside this region which is scaling. So you think of a space which is kind of flat in most of space. That's kind of always true. I think when you say you take the asymptotic, when you could draw the Penrose diagram, most of space is vacuum.
But I guess the worry here is since we want to go towards a statement of holography, right?
Yeah.
The order of limits is the issue, and one wants a screen which will capture most of what is going on.
I don't think that even happens if
That's why I think the worry is there.
I think this, even in flat space, if you want to measure the energy, for instance, if you're very careful about fluctuation, you really have to measure the energy from R to 2R or R to 10R, and then take that whole shell off to infinity. So in fact, even in flat space, even for massless particles, this is just a fact about measuring the energy.
Well, say that statement again.
This is related to a different story. If you just want to measure the energy, you could ask, if you measure the energy just in some region R, and you just put a sharp cutoff and measure the energy in this region, this quantum field says statement, take R to infinity. You'll find, this has a large fluctuations in the vacuum. If you just measure the energy by integrating the stress tensor from in the region R. So in fact, a good way to measure the energy is you measure the energy from R to R to 100R, and then take this whole shell off to infinity. So what you do by that is you measure the energy that's inside, but in fact you assume there's a large region where nothing is happening, which is R to 100. So in fact you could say you miss like 99. So this is true, I think, even if you want to physically measure the energy, that you have to assume that stuff is happening inside, and you have to have a very thick shell. Shell is very thick, yeah.
But just to say, ADS is different in this regard.
ADS might be different. It is true because the metric behaves differently.
Because the stuff you're losing is very high energies.
Yeah, it could be that ADS is
because of the redshift factor.
It's very high energy.
It's very high energies. So here it's all equal energy.
Yeah, it could be. But I think it's reasonable to say that you focus on some region and then you go off to it. You take a shell, which is true. But okay, we could discuss that.
Yeah.
After this arithmetic is translation variance. So every point is same as every other one. So even if it's focused on one operators which were interacting in one region. So I find it hard this argument, but if you take arithmetic, translation invariance is there.
Yeah. So you'd be able to reproduce what happens.
Reproduce
what happens. However, just along the lines of our paper, you do an arbitrary S matrix, for instance. I mean, it's different. It's time thing. You know that the interaction sometimes happens at rho by 2. You know, so you would lose something.
So I'll say something about interactions though, but yeah, but maybe
okay.
I'll say a lot about hopefully. Okay, good. Let me say something about bulk. Since you already had this discussion, if I want to write bulk fields after I've taken this rho goes to infinity, I can in fact write them as smeared boundary operator. I'll put a cutoff at 5. Is that good or is that too late? 5 is fine. Right? Okay, fine. Okay, good.
You can go on.
I'll stop it. I'll certainly stop it. Yeah. Okay. So we already went through, 1.5 months. Yeah. Okay. So let's say I want to reconstruct operators at finite R, and now I'm still saying something about free fields. In fact, I can do some analog of HKLL reconstruction, which is I can write an operator R in terms of operators on the boundary. This is subject to all the caveats that we said, right? These operators you can think of as being order 1 compared to rho. So the idea is that you want to write an operator finite R, you take this boundary operator, which is an operator on de Sitter, and then you integrate it with a smearing function that's a function of the bulk point and the de Sitter point. And you integrate over de Sitter. This smearing function is what in ADS is called the HKLL smearing function. We can also find it explicitly. For us, it's this. It's a very simple explicit form, in fact. Okay? This is what's called the modified spherical Bessel function. Which means, it's the modified Bessel function. It's modified Bessel function. This is like KL plus half of x by square root x. Where k is the modified Bessel function. Okay, that's the small k. So we can explicitly find this HKL type smearing curve, and it's this. So I take this boundary operator, I integrate it with this function. I'll get an operator that behaves like a bulk operator in free field. Okay. Good. Let me say something about bulk locality. This will be relevant in the end when we come back.
Sorry, one question. I mean, maybe you come to interactions.
Yes.
So there's this delta function in interactions, which
what delta function?
Momentum conserving delta function. Does that give you some structure in your correlators?
It will appear in what we'll say, but I'm not. Maybe you can ask the question again. I'm not sure what structure.
I mean, in ADS CFD, the fact that you have this momentum conserving delta function gives you singularities and correlators.
Oh, that's a good point. Oh, we don't know actually. Maybe that's a good. Is there some analog of some even a bulk singularity? I don't know actually. That's a good thing. We should think. I'll show you something special. Okay, good. So consider some functions that satisfy this. So remember these functions have to be analytic. What's an example of a function that's analytic? It's e to the minus cos tau. See, it dies off faster than e to the minus 1 over delta cos tau. So it dies off very fast at large tau. Okay, such a function which dies off very fast at large tau, which is a function of very sharply peaked. So it's almost like it's peaked about the middle of this de Sitter space. Almost what the relativists would be happy with, although it really has support to tau goes to plus and minus infinity. Such a function has the property that if you take it and you smear it with a boundary operator, then it commutes with most operators inside a large ball in the bulk. Which is kind of intuitive. You take something, you take the smearing function, and you integrate the boundary operator very close here in a very small time band here. This is what in ADS would be a small time band. This is an analog of a small time band, a sharply peaked smearing function. Then most operators in the bulk, they commute with this. So this is, it kind of creates operators very close to the boundary. This is what in ADS you would say. If you give me a small time band, you would create operators close to the boundary. This is the analog.
It creates a very thick shell, very diffuse shell.
You mean this shell, the smearing function?
No, the smearing function will create some shell of the field that goes in.
Yes, it's very diffuse. It's right. It's very diffuse because there's infinite space. But it still commutes with things which are there's sharp locality. It commutes with everything which is in the middle.
Because
that's right. Okay. That's right. So you can say close to the boundary, or yeah.
Sorry, but just I mean it's very peaked in the time direction. If I'm right, because this is
the smearing function. What Shiraz is saying is it's very diffuse in that what I've drawn is a small pink band is actually much bigger than the blue ring. Because it's actually rho, it's everything out for rho larger than 1 by twice m delta. But that's actually infinity. So even though I drew it this way in these coordinate systems, I should really have drawn it That's that being infinitely large and the blue being small. But okay.
It's like zero size would be a bulk to boundary propagator, which would spread everywhere.
I mean, so you've taken a very tiny band, right? And it's out at rho going to infinity.
Yeah. By the way, this is also true in ADS, that there's infinite volume near the boundary.
But it's all high energy.
Yeah, it's high energy, but there's still infinite volume there. So if you were to draw it in the coordinate system, you'd get infinite. Yeah.
Yes, I agree.
Yeah,
It's physically different.
Yeah, okay. Right. Yeah.
I said, but just to understand, okay, you're out at large rho, you take a tiny band. So just by causality, you can't affect very.
That's exactly what's happening here.
And so then that's what I thought.
That's exactly what's happening here.
It's coming
This comes from causality. This is exactly what's happening here. It's coming from causality. But this band is actually, it's smeared over. You're right. It's smeared over. But remember, this tau is weighted with a factor of rho. So it's a tiny band in tau. But it's actually a big band in the Minkowski band.
Everything we're looking at is space-like.
No. It's not space-like separated. Maybe there's something I should have emphasized here. You see, these taus, this integral here goes over all tau.
Okay.
So in fact, you could have asked, how did I get an operator here by integrating over something that was space-like? That's because I'm not integrating over something that's always space-like. Remember, this decimal 3 is really going, is this slice, it's this red slice. So the way I'm able to reconstruct something in the middle is by smearing something over this full red slice.
But if I look at the center.
If you look at the center, it's space-like.
Yeah.
But there are no smearing, there are no compactly supported operators on this boundary because everything has to be smeared with these analytic smearing functions. So the best I can get to a compactly supported operator is taking a function which is either doubly exponentially. Yeah. This is my function which is analytic and is close to being compactly. Then it fulfills this intuition.
So I thought the whole point of this e to the power m rho was that you're compensating for the fact that it's tunneling through a space-like things.
You're compensating for the fact that it's tunneling through a space like that might be the case, but you still can't violate microcausality. I mean, it's true that it's fine. So, if you want to reconstruct something here, you have to smear over something else.
That I agree. Oh, fine. But I just wanted to say that the way I think of this problem is that if you have a laser, suppose I wanted to shoot a laser at Mars. If I make the laser very thin, it will go diffuse. By diffraction. You make the laser broad, you'll be able to shoot it more accurately. I think it's sort of there.
Yes, I didn't understand, but okay, maybe you can explain to me later. Yeah. Okay, this I didn't see, but maybe we can.
But I cannot quite translate your thing, but he's made it very sharp in tau.
Yeah, your intuition was right. You make it sharp in tau, and therefore it can't affect things which are far away in the boundary. Although there's some leakage in tau because it really goes to tau equal to infinity. Okay. But the point is that leakage is small enough, then that gives you a sharp microcausality in the bulk. It really doesn't affect anything. Okay, good. Let me say something about interactions now. So I said everything I could say about the free field theory. There is actually nothing more you can say. There are no more, I don't think any more questions to ask. Because remember what I said is I defined these operators. I told you how you had to smear them. I gave you the 2-point function. I told you how to reconstruct bulk operators in terms of boundary operators. There's no more question to ask. Okay, that's all you have to say in the free field theory because there isn't anything more. The n-point function factorizes into product of 2-point functions. So I told you everything about the free field theory. Now let me ask questions about interacting particles at spatial infinity. Of course, if this was all about the free field theory, it would be boring. So I have to say something about interacting. Good. Now, the first thing I want to say is I want to study Weitmann functions and then take the limit of Weitmann functions going to infinity. Why do I want to take Weitmann functions? Well, the reason is, Weitmann functions might be slightly less familiar to you than time-ordered functions, but they are actually kind of the most natural thing from an operator algebra point of view. I just take a product of fields in the bulk, just a product, I don't time order, I don't do anything, and I just take the correlator of that. That is what I'll call W psi one side. This is called a Weitmann function because I picked the ordering by hand. I didn't declare it to be time-ordered or anti-time ordered. Okay. Now, why don't I think of time-ordered functions? Well, remember, I want to smear my operators with these analytic smearing functions. Time-ordered functions always have a theta of T2 minus T1. That's how you define time-ordered. And that spoils these analyticity properties. So it's difficult to define the limit of time-ordered correlators even in the free field theory. And so we don't want to do that. Second, from the algebraic point of view, Weitmann functions are natural because that's what defines an algebra. That's the natural product structure and operators of the Weitmann. Just multiply things. Okay, good. So I'm going to study Weitmann functions. The disadvantage of this, we have the world's experts on this in ICTS. We are not. But is that you have to. It's very complicated to do this in perturbation theory. That's because for these Weitmann functions you have to have. Yeah, Loganite is the world's expert. Yeah. So we have the world's experts in that. So Loganite, so we go and ask them questions when we need to, and they tell us when we can understand the notation. But there's a lot of formalism that's been developed to understand this. In fact, a lot of it developed by Loga and friends. And the point is that to compute these Weightman functions, you have to go back and forth in these contours. It's not a simple contour like the time-ordered correlators. You have to do something complicated. But anyway, you can do it if you have two postdocs and students working on it. Then you're able to do it. They can go back and forth the contours, and we can do lots of calculations. But it's hard.
Orderings are in tau or in?
There's no ordering. It's just T.
When you say time ordering or not,
it would be the same. Time T and tau would be the same because it's time ordering is.
Could I ask you a question about one thing? When you do the smearing function over your wave function, do you have is it possible to display a one-parameter set of wave function answers with this width of smearing?
What do you mean one-parameter family wave function answers? What
meaning
this
when
was a
you
2-point function?
Yeah, but let's take a 1-point function. I just want to see what operator you're taking.
One-point function of what?
The smeared operator. It's associated. It's a coefficient of some wave function.
Oh, it's a coefficient of some wave function. Yeah, sure. You could do that.
Shiraz, are you saying?
I want to check with my intuition.
Maybe this was one case is smeared operator.
Can I just ask if Shiraz meant this? Take the field phi, expand it in usual Minkowski codes.
Yes.
Then smear it against whatever he's doing. See what it is. That's what
I was thinking this would be
how these
things look. And you were talking about this one parameter.
How these plane waves would look. How a plane wave would look, for instance, if we smeared it. I could tell you what that is. How e to the ikx would behave if you smeared it.
You're smearing against something, right?
I'm smearing against its g of x. That's my smearing function, g of x. G of x is a function of all of, so it's really labeled by the function. And I can tell you what a plane wave would look like.
No, but you want to pick some nice functions, right?
Nice functions have analytic functions. No. The only characteristic on G is it has to be analytic.
And you had a one parameter set of focusing.
Nothing else. G. That was later. I said you could make them, but you could choose not to. The only constraint here was G is analytic in tau.
Yeah. Let's say you did that with a one parameter set, which was
one over delta.
How much?
1 over delta.
Yeah.
I could.
That's what.
Yeah.
So what you want to ask is what happens if you take a plane wave, which is e to the ik rho x. This is a plane wave, and you integrate it with one of these functions. Right? Is this the kind of question you want to ask?
Fine, yeah, sure.
This is the kind of question. I don't remember the answer offhand, but this will roughly give you f of tau naught.
Ik rho x.
Well, that's the plane wave in the past because it's rho times the de Sitter coordinate. So it's e to the I 4 vector. Let me take it on shell. This 4 vector, 4 momentum is on shell times rho x.
I see.
This will, I think, give you f to the tau naught plus I pi by q into I L the omega hat. If I remember, k. But this tau naught is related by some since tau naught is equal to mod k. I don't know this sense. Maybe I.
In order to get finite point function, this works only with certain g's, right?
No, any g that's analytic.
Any g that is
analytic.
So then let me ask this question again. So what about the support of this G where the two particles are kind of close to each other?
Yeah. So
that would be infinity, right?
No. So you're right that this G smearing with these analytic functions gets rid of this. I don't know how so indeed smearing with these you see maybe this is a good way to think. Think of what the 2-point function here is doing. What it's doing is it's giving you a delta of tau 1 plus tau 2 plus I pi. So it's forcing. If you write this 2-point function as a delta function, it basically forces the points to be such that the distance between them is 2. So it forces the points to be antipodal. And that's something that the analytic functions do. I don't have a very clear answer to.
I mean, if it would be, I would agree with it if the configuration space there were no points where it is less.
I see your point. It's true that the analytic functions force you to they force you to be on a point where the distance is exactly twice so. So this is true that they give you these delta functions. If you look at this, I don't know how to say it. Yeah, in a
question I would ask is take the propagator from this point to that point and smear it with your smearing function.
Yeah,
and look at it as a function of this.
Yeah, and you will get this answer. I mean, you will get the answer.
Yes. No, that's the question. How does it look? The propagator as a function of this, just with one. if every one of these
That
focuses
might
near
be
the
this
origin,
question. That's probably the scale.
then it is.
That's probably
It
this.
works for every analytic.
But
Yeah,
many
it's any
analytic
analytic.
functions do this.
Analytic functions do this. It works for any analytic function is a fact. I'm not quite being able to translate into.
So is it true
You're asking why do
that
they
focuses near the origin? Take the
This is
propagator.
harder for me. Actually, this is the language that you were saying earlier also, but it's harder for me to translate this into the statement that any analytic function focuses on the origin. But it sounds physically that that's the right thing that's doing.
But it should be easy to check.
I don't think it's true that every analytic function will. What do you mean by focuses on the origin? Like
Meaning that the way that I do the smearing here, I look at this as a function of here, and then it exponentially dies off as you move away.
So you want to look at phi of x times something like this, then it x f of x.
Let's take the propagator. It's a 2-point function.
The 2 point.
What is z? What is x?
Z is the boundary operator. This is capital. I smeared it with something.
Bulk boundary property.
Bulk to boundary propagator.
It's
Great.
the bulk to boundary property.
Perfect and smear. Yeah. And I want to look at it as a function of the bulk point. Yeah.
Of this bulk point.
Yeah.
Yeah, and this will certainly have a right. So and now you want to ask how does it behave?
How does it behave as a function of
As a
x
function of
as you move away from
the
it?
bulk point, right?
Yeah.
That's probably something we can read off from here. I don't know if I want to do it live.
But it should be exponentially decaying. Otherwise,
As exponentially leaking as you move away from the origin. Yeah. So it should be either the minus m rho, you say.
Why is origin being picked at all?
They-
There is
they have
nothing
one
in
fixed
that.
origin.
There is nothing in the on the boundary. Origin is not being
No, it is being.
signaled out,
It
right?
is being. Of course, it being.
Because the analytic there.
Well, you
No, you said analytic, but you're working this for we broke translational invariance from the start, right? And we took the extrapolated. So something is speaking of the origin. The origin is being picked up. You're asking if this decays in e to the minus m rho automatically.
or larger.
Yeah, this without smearing the other side, this might be true. I'll have to think a little bit more about it. It might be that this is the correct way.
Then that would be the focus.
Yeah, it might be that this is the way I think. But this is something we can check easily, but I don't want to try and do that here.
So sorry, Shiva, just to understand, so your point is then this kind of focusing, therefore you picks up this region.
Then this explains the question.
That it does.
You are therefore picking.
This might be correct. This might be true. Okay, good. There's a fact I'm getting confused about, but this might be correct. Yeah. Okay, good. Okay, let me say something about interactions. Okay. So we want to study Whiteman functions and now understand interactions. The first thing about interactions is that, in the interacting theory, if you just compute these Whiteman functions, bare Whiteman functions, you will find that they do not die off like e to the minus n rho. And just smearing is not sufficient to let them die off as e to the minus n rho. There's in fact a pretty simple reason for this. The reason for this is that, sometimes we want to think of intuition of having some massive particles far away as m. And we want to think of, correlators dying off as e to the minus n rho. But remember, in this Whiteman function, if you just compute the Whiteman correlator, you have all sorts of virtual particles that are probable. And some of the virtual modes have support in time-like momenta, which have k squared, which is smaller than n. Okay. So in fact, if you just compute naively the Whiteman function and look at how it behaves at large rho, there's some Laplace transform you can write down. It looks like mu of gamma times e to the minus gamma rho. This mu of gamma has a delta function at gamma equal to m, but it also has terms which have gamma smaller than m and gamma larger than m. Okay. The terms which have gamma smaller than n will kill you because they're telling you that the interacting fall-off is much slower than the free fall. This is just something you can directly do. So if you just take naively the interacting correlators, it doesn't work. Okay. The solution is no. You see, everything will fall off as m, but what do you mean by n? M has to do with the mass of the particle, but the particle is not on shell. The field far away is not on shell, because the field far away is just a field operator, and it contains all sorts of excitations, including some which are not on shell. The parts which are not on shell can die off slower than e to the minus n.
Well, it should die with the physical. So I can agree that's different.
No. The physical, no, because you're not putting it on shell by taking it to spatial infinity. When you go to plus, I plus and I minus, you naturally put things on shell. So in fact, the solution will be indeed that you put things on shell. If you put things on shell, this will go away. So these properties, another way to say it is these terms which are not dying off as e to the minus n rho are not independent of field redefinitions. They depend on what field what fields you put in.
Just physically, shouldn't it be that, let's say there is a physical particle, that things should fall off with that?
Except
even in spatial infinity.
that you'll have to define a quantity that's independent of field redefinitions. You'll have to pick up an operator which is sensitive to the physical particle. Just taking operators, your field operators, and pushing them off to infinity doesn't pick up the physical particle, doesn't pick up the pole. So in fact, the solution I'm going to say is you pick up that pole.
But is this true also for time-ordered correlators?
This is certainly true for time-ordered correlators.
I also find it puzzling.
But why? I mean, this is just the fact that you take it's this fact actually.
You take sort of LSC you are putting in.
I'm going to do an LSZ. Right now, I'm not done in LSZ.
Before LSZ, I thought that e to the power minus n rho will happen.
If you just take e to the ik dot x, which is you think of some correlator, think of its Fourier transform.
Right.
And now what? So this is e to the ik rho x, and I have to smear it integrated to this function f of x, and then I have to take rho to infinity. What tells you that this will fall off as e to the minus m rho if k squared is not equal to m squared? Now, k squared would be smaller than, in fact, if you look at time-ordered correlators, they have support for all values of k squared. In the case when you have the free field theory, this correlator has support only when k squared is equal to m squared. And then when you do this integral, this falls off as e to the minus m rho. In general, this falls off as e to the minus square root of k squared.
Those with larger m
doesn't matter. That is smaller. Yeah. But there are things which have smaller m.
But in the Lehmann representation, if you've got a stable particle,
yes,
the lowest will be the most.
No, but that's not true for the Fourier transform of correlators. What you're talking about is true for the spectral, if you look at the spectrum. But if you just look at the Fourier support of correlation functions, so you just look at the time-ordered correlator, it looks like 1 by k square minus m square plus I epsilon. It has support for all k square.
For the 2-point function, will it be?
Yeah, look at the 2-point function. Look at the 2-point function, the time-ordered 2-point function has this form.
Right.
It has support for all values of k, including k square not equal to m square. It has a delta function at k square equal to m square,
right,
but also has support for k square smaller than m square.
Right.
So if you just push it off to infinity, you will find it doesn't fall off. It falls off this way.
This is true even just for one single free particle.
This is true for free particles. The time-ordered correlator actually doesn't have a good limit. Everything I did, it was important for me to take the Weightman function, which actually looks like delta of k square minus m, which really forces the Fourier transform to be on shell.
But the free particle,
the time-ordered correlator does not have a good limit as you go to spatial infinity.
No, but this e to the minus m rho kind of behavior for free particle you had it, right?
For free particles, I had it for a free field, for a single field. If you now start looking at 2-point functions, then the 2-point time-ordered function looks like 1 by k square minus m squared. So it has support for all values of Fourier momenta, and the large rho behavior is e to the square root k squared.
This Fourier transform is propagator.
Yes,
and you take your IHs.
You take your IHs. You'll get a delta k square minus m squared, and then you will find that there's some additional terms which fall off slower at large. It's actually pretty simple to do this. The way you do this is you look at e to the k rho, and you have to pick up a saddle point in the integral over the global time, over the de Sitter time. And that saddle point, you see, how can this fall off as e to the minus m rho? There's no m here.
No,
this k can be what?
So,
forget about this delta k squared.
I was saying that in 1 over p square minus m square, we do the p0 integral by the Cauchy square.
The p0
integral, you use the Cauchy vector pole to do the p0 integral. That will introduce m in the exponent.
Okay.
And then you do the other 3 momenta integral.
Yeah.
That will basically make you e to the power n. The distance.
All larger, yeah.
No. I think this. 1 second. Let's. No. You want to do the k0? Okay. Let's look at do we have to look at a 2-point function, or are we allowed to look at higher point functions? Let's look at some interacting, because I want to talk about the interactions. Then the statement is just this. The correlator you have is this. Unless you're going to say that higher point functions somehow are always going to have support only on k squared equal to m squared, which is not true in general.
In a Euclidean theory, is it true that just Euclidean that things don't die out like e to the power minus m?
Where would n come from? In general, for a higher point function, I know, but for high point function, the general Euclidean correlator has support for all kinds of momenta, which don't necessarily know about n.
No, but I have 4 positions. Let's say x1, x2, x3, x4.
Yeah.
I take all of these guys separated very far away.
Yeah. And so this is the answer you'll get. You'll get some answer which will look like, and Fourier space is easy because it lets you analyze the follow-up. This is a true statement. You do this integral, and you get a follow-up which looks like equal square.
Shouldn't it be, even by your reckoning, there should be an m square there, right? The propagator.
This is just a statement about integrating plane waves with these analytic functions. They fall off like e to the minus square root k squared times 4. Because there's no m here, not a quantum field theory. So it's a statement about just looking at the fall off of a plane wave which is focused. And there's no m here. So unless you're going to tell me that you look at a correlator which is off shell, and somehow it is only going to have support for k squared equal to m squared, it can't be that the fall off is e to the minus m.
Coming from the P0 integral.
But P0 integral, maybe you want to do this for a 2-point function. I don't think it will actually for 2-point function also. I think if you do this, let's just look at a general n-point function.
N-point function also, you do it in like take bulk boundary operator for each.
It's not true that the n-point function will have support only on k squared equal to m squared. It's just not true that the n-point function is supported on mass shell. N-point function in Fourier space is not supported on mass shell.
This contact diagram.
I don't think the n-point function even for contact diagram is supported on mass shell. What you want to say is the Fourier transform of the n-point function has support as a delta function on mass shell. I don't think that's true. It has other terms which don't live in mass shell. In your case, what you want to argue is the principal value term in the 2-point function doesn't contribute. There's a delta function which you're picking up. You want to argue that the principal value doesn't contribute. I don't think that's true even for the 2-point function. If I write the principal, the 1 by k square as the principal value plus a delta function, the delta function is the one you want to pick up. And you want to say the principal value doesn't contribute, I don't think that's true.
I'll try once more, but you must go on, and I'm very sorry. If you think naively in terms of Green's functions, right, in Euclidean space, your Green's function is 1 over k squared plus m squared, right? You put it up, e to the minus s k squared plus m squared, e to the I k dot x, blah, blah, blah. Ultimately, you get e to the minus m x squared. This is what happens, right?
E to the minus
m distance.
E to the minus m times distance is correct for the 2-point function. It's true that 2-point function looks like e to the minus m. First of all, it looks like e to the minus m into x1 minus x2. It doesn't look like m distance. It looks like m into x1 minus x2.
That's what I meant.
Now I have to take, I want an e to the minus m row in every term. I don't want some overall e to the minus m. So I want an e to the minus m row in every term. So this is the term, this is the problem I was trying to cure by integrating with my analytic functions. Because it looked like e to the minus m x1 minus x2. What I wanted it to look like was e to the minus m x1, e to the minus m x2.
The caudal distance versus the.
Yeah, so this was the caudal distance. This was
That's what
This we understand.
This is fine. But now I wanted to make this.
This we understand. That's the point that I
now you want to say that for n-point function it should look like this minus mx and really it won't. So I want to make it.
So then I was not understanding.
Even I was not.
Okay, so you see, because my renormalization is I'm going to scale I have a renormalization factor for every field, right?
Yeah.
So if there's just some e to the minus m times some factor, that's not helpful for me. I want to define some boundary operators once and for all.
No, but that's what I was asking. I mean, that I thought your smearing is supposed to take care of that.
I want
That is focusing and.
but it won't work for an n-point function. For a 2-point function, it did work.
But if focusing was correct, it should work also.
It also should.
Well, so focusing, it's not clear because, when you focus, you might have backscattering in the region where you're focusing. So it's not clear that, focusing is something that's meaningful in interacting.
In the free theory.
In the free theory, it will work. You can focus so easily in the.
You say you're trying to focus, but there's an interaction well before.
As you are doing that.
So it's not present focusing. So this focusing thing, I don't think it's this focusing, but if I have to think, this is what
Fine.
this backscattering looks for.
Oh,
So
so
it's-
it looks, yeah, okay.
Okay, so I'm going to give you I'm going to say you basically focus on this part, on this delta function part. So I'm now going to give you a prescription. Prescription is as follows, okay? Take this Weightman function. This Weightman function has the following structural form. It looks like a term which has a product. So look at this Fourier transform. It looks like a term which has a product of delta functions in each of the external momenta. This is the term which is on shell. Plus it has other terms. These other terms depend on field redefinition ambiguities. This term does not. I want to say focus on this term and throw away the other term. That's like saying focus on the part which goes like e to the minus m row and throw away the other terms. Okay, although that's not.
That's not what it says, right? That just says that it's like LSC.
This is like LSC. So you focus on the K square equal to M square. It's
But
slightly
the
different
position
from this.
space dependence would continue to be
Not
on the coordinate.
if you do this and then you do the smearing, if you do the LSZ, you pick the on-shell part and then you do the smearing, then you will have good follow. It just comes from this formula.
Yeah.
You know, it's the fact that if your Fourier transform, your Fourier momenta are focused on K square equal to M square.
You're looking at the analytic continuation of the S matrix.
It's not quite, I'll say how it's related to the S matrix, not quite the analytic continuation. I'm going to say what this is. This is a Weitman function, I'll relate to the S matrix. But right now it's just this. You look at the Weitman function, you focus on the on-shell part, which is like LSZ. So you see in LSZ, you pick out the residues of the poles. Weitman functions don't just have poles, they have delta functions also sometimes which come separately from poles. And so the analog of LSZ for a Weitman function, this is like LSZ, but it's the analog of LSZ is you pick up the coefficient of the delta function. By the way, I could have framed LSZ also this way. I could have said, look at the time-ordered correlator, look at the coefficient of the delta function. That's not how we say it. But here I'm saying, look at the Weitman correlator, look at the coefficient of the delta function.
But is it true? Is it clear that there would be such terms in the
There, absolutely. Every time-ordered correlator will have such a term, and every Weitman correlator also. So there will be such terms. I'll say something. This is a very interesting. It's a pretty interesting object. It's related to the S matrix. I'll tell you what this object is. So focus on this guy. This is the on-shell part. It's like doing an LSZ reduction of the correlator. Then take the extrapolate limit. So this guy, which is the on-shell part, which I want to call WI0. So it's different from W. It's the on-shell part. The LSZ reduction has a good boundary limit. So you take it to infinity. Then you have to do the smearing. The smearing is not gone. You have to do the smearing. So you do the LSZ and the smearing. You get a good interacting. Okay, here's another way to say this. Okay, this is a question we could have asked in quantum field theory a long time back, and we are surprised to know this question had not been asked. You see, in the free field theory, we know the free field theory has a.
Just to ask you, does this mean you're only keeping some of the information in your?
It might be we're keeping all of the information because the on-shell part might have all. It's like the S matrix. The S matrix you can say keeps only some of the information in correlators. We haven't proved this, but we think it kind of keeps all the invariant information.
Because on the face of it, it seems to only keep part of the.
That's also true of the S matrix. You could have said it keeps the residue of the pole, but we don't usually think correlators have more information in the S matrix. Some field definition. What I said right now is a slogan. It's true that on the face of it, we are keeping only part of the information, but we hope it's all. Okay. You see, you could have taken take the full Heisenberg operator and ask what is the on-shell part of the Heisenberg operator. When you Fourier transform the Heisenberg operator, what is the part that has a delta of k square minus m square? This is a question which in the free field theory it is the field itself. The full field has a delta of k square. In the interacting theory, what is this object? So it's this object we want to focus on. So pull out the coefficient of the full Fourier transform, the full Heisenberg operator, pull out the part which is on shell, and make this free field like object, which is just taking the part which is the delta of k square minus m square. And look at correlators of that object.
This throws away the extra because it only keeps the part that is one part.
Yeah, that's right. Yeah, but it'll have a lot. It's quite an interesting object. It is related to the S matrix. Okay. So this is the correlator. This is how the analog of LSZ. Except we are doing this at the level of the field operator. So this could is a question. It's kind of a natural.
What exactly
You take the full field Heisenberg field operator. You integrate it in mass shell. So you integrate and also about negative omega. So this is phi plus and phi minus, and then you put these components together in a field. This is an on-shell field. It satisfies the Klein-Gordon equation. But it's actually an interacting field. It has non-trivial correlate. So it has not, even though it satisfies the Klein-Gordon equation, every variable, it has non-trivial. Okay, so this is the object. And as I said, this is natural question quantum field theory you could have asked. What is the on-shell part of the field? That's the guy who we are looking at.
So this definition doesn't single out the origin, right?
This definition doesn't single out the origin. This is just the definition momentum space. And now we're going to go back to spatial input.
But you're saying if you do things with this operator,
it gives you something which behaves nicely as you go to spatial input.
It's like, but that's an origin specific statement.
That's an origin specific statement. It's just, I don't know why you said. In the end, the operators we define as spatial infinity, which are the ones I'm defining here. For these we picked up, it breaks translation invariance, but these operators transform nicely under translations. I mean, we are breaking translation invariance. But if you tell me if you picked a different origin, I'll tell you what new operators you get. It just multiplies the smearing function with some factor. So it's not like, it's true we broke translation invariance in taking the limit, but it's not like we know how things transform.
Oh, there's still that, yeah.
Yeah. So now you could ask, if I give you these operators phi plus and phi minus, what are the original operators z of f? I spent all this talk talking about these operators z of f. So this is how the operators z of f are related to phi plus and phi minus. Okay. You have to take this phi plus of k. This tau is just related to m sin tau.
I lost. What is phi plus? What is phi minus?
Phi plus is just the positive frequency part of the on-shell part, and phi minus is the negative frequency. So it's like the interacting creation and annihilation operator. And I'll say what they are in simpler language. Yeah.
Just make completely sure. So the left hand side is the k, and omega is square root of k square plus physical mass square.
Omega square root of k square plus physical mass square. The full renormalized theory. Exactly, the full renormalized physical mass. And then I just want to say these phi. I'll actually now start talking about the phi plus and phi minus. But in the back of my mind, I have this z of f, and the z of f is related to phi plus and phi minus. There's a basis transform between phi plus and phi minus and z of f. But if I tell you all correlators of phi plus and phi minus, I'll give you correlators of z of f.
So it's like projecting phi onto the one particle space.
It's not one particle. See, I'll tell you what this phi. Can I say one more thing and then I'll say? So maybe this is the answer to your question. You can ask, what are these phi plus and phi minus operators in terms of the in and out operators? Okay. So remember, there are in operators and out operators. The in operators are defined at I minus, the out operators are defined at I plus. We want to think of these phi plus operators as defined at I naught. How are they related to the in out operators? The answer is very nice actually. I won't prove it for you, but it's the following. Phi plus is just half of the sum of the creation operators here and there. And phi minus is half of the sum of the annihilation operators here and there. Okay, so if A is the operator at I minus and B is the operator at I plus, then this phi plus is A plus B and this is A plus B annihilation. Now this is not
all for one particle.
This is the full operator for one particle. This is the one particle creation operator. Yeah. But notice this has all sorts of interesting information about interactions because the A's and the B's have all sorts of complicated commutation relations. Remember, the A dagger is a delta function, the B dagger is a delta function. But if you look at A plus B and A dagger plus B dagger, that's very interesting. That doesn't have a simple relation. So if you start looking at correlators of these guys, they'll in fact give you the full, they'll give you a lot of information about the S matrix, as I'll show you.
How did you define A and B precisely? You go off very far in the future, quantize the field on.
The way we define the S matrix. In the S matrix, we define A and B. We go very far in the future, very far in the past. A is what creates in states from the vacuum. B is what creates out states from the vacuum. So you look at the overlap. So A and B are what you use in the S matrix. And the operators at I naught are kind of naturally an average of A and B, which is nice. The averages of A and B. So this is, I won't prove the formula, but it's pretty simple to prove this. Okay? That this is how these operators behave.
And these are A and B's are in the interacting theory.
Full interacting theory. Yeah. This is a full Heisenberg operator. So A is the full operator at I minus, B is the full operator at I plus. So these are operators you use to define the S matrix, and phi naught is the arithmetic mean of them. Okay. Now, by the way, interestingly,
I mean, it's far from clear to me that this seems to be happening.
I can show you how this proof happens, but it's pretty simple to see. Interestingly, correlators of this kind were studied for a very different reason by Caron-Huot et al. In a paper last year. And they studied correlators of operators of this kind. In fact, they had general linear combinations. So the correlators we are defining at I naught are a subset of the correlators they define from a completely different motivation. We came to it by thinking of I naught. So we try to define some operators that have a good limit, but they are, these correlators have been studied in the literature. Does this answer the question you had of this phi plus and phi minus?
Perhaps it does. But A in terms of B is a multi-particle operator,
yes,
right?
Yes.
So I'm confused. I mean, you were sort of projecting on the single particle state.
I was not projecting onto single particle states. I was projecting onto the mass shell. What satisfied K square D? That's not single particle states.
K square equals M square, right?
Yes.
But one particle.
But one particle M. That's right. So B and A both give you both have K square equal to M square.
Even though there might be multi-particle.
In terms of one or the other.
One.
Yeah.
So how can that be?
Well, because it's no. That's because B would be A dagger into A's and so on. It would not be product of A daggers. It would be A dagger times A and something. So it would be something which would have K square equal to M square, but it would not just be product of A daggers.
I see. No, but I mean in normal S matrix.
Yeah. Normal S matrix, you look at B's on one side and A daggers on one side. You never look at these kinds of combinations. Kind of a funny combination. In normal S matrix, you take A daggers on the right and you take B's on the left, and you never act with B daggers on the left, and never act with A daggers, and never act with A's on the right. This is what normal S matrix is: B, 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 A dagger, A dagger, A dagger. This is normal.
I suppose that's answer. Thank you.
Okay.
So improving these is important that the phi satisfy the client part.
No, this was a definition of phi plus, right? The phi itself was a full Heisenberg operator. Then I defined phi. You see, I'm asking the following question. Take the full Heisenberg operator. What is the part of the operator that satisfies the Klein-Gordon equation?
Sure.
Right?
But then that goes into the proof.
And that is this. Yeah, that's it. And that is, if I claim in the full interacting theory, the part, it's a question you could have asked in, you could have put in QFT textbooks. But it's not good.
That you write down some Klein-Gordon in a content.
Well, proof actually comes from Feynman diagrams. It comes from the fact that you look at the perturbation theory for this phi plus and phi minus, and it turns out to match the perturbation theory for these operators. That's the proof that we have. So, it's kind of, natural question QFT. This is the answer.
Verifying these fields given, what is M?
Huh?
You choose any M, right? And on the M.
You could choose any
M square between.
No. Most fields would not even have a supported k square plus m square. You have to take a field which has these, which corresponds, which can create one particle states of mass m. Only such a field will have this. Yeah. Okay, so this algebra at I naught is non-trivial when external states are set to the vacuum. Unlike the algebra at I plus and I minus. By the way, that's one nice thing. It's related to a question that Shiraz asked in the beginning. You see, the algebra at I plus and I plus looks like it's a trivial algebra. This algebra at I naught keeps track of interactions. And this is nice because it's reminiscent of ADS. In ADS, if you look at the boundary algebra, it keeps track of interactions. In the boundary algebra at I plus, we didn't have any sign of it. It was a free algebra. You could say things about, where information was localized, but it didn't keep track of interaction. So this is kind of nice. This is just a comment. So this algebra is non-trivial. Let me give you some examples of correlators computed with this. For instance, you can here's the correlator. Okay, you put phi pluses on the right and phi minuses on the left, and you find the following answer. You can put different combinations. You can put 5 different things. But this is the 4-point correlator that's non-trivial. It looks like out in plus in out, or in out plus out in. Okay. This you can check, in fact, is the real part of the S matrix, or is the imaginary part of the T matrix. And the way you see that is, out in is like the complex conjugate of in out, and then you use CPT to match, to flip the states from right to left. Okay. So this is the real part of the S matrix for the 4-point function. And you can compute in perturbation theory using these horrible Schwinger-Keldysh things or nice Schwinger-Keldysh things. Depending on what you ask, and you will find indeed this answer matches. Okay, you can also study cases where you prepare some non-trivial in and out states and then you measure states at I naught. So that's the physical thing is you prepare a state at I minus, you make some measurement at I naught, and then you measure something at I plus. So you can also measure correlators of this kind, which are psi1, insertions at I naught, and something at psi2, some final state. So it's a combination of an S matrix and this set of operators at I. I'll give you an example. For instance, let's say I prepared a 2-particle out state, 1-particle in state, and I measured this phi minus. Then you will find it would this correlator, which is actually a correlator which has insertions at all 3 points, is exactly the S matrix, is the in out. Okay. And you can just verify this easily by putting in the formula. Okay, then you can go to higher points. If you go to higher points, things become complicated. Let me say something about contact interactions, since this is something that was asked. You could ask, what about contact interactions? Okay, how do contact interactions contribute to these correlators at I naught? In fact, contact interactions are pretty bad in Schwinger-Keldysh. A 3-point contact interaction already requires you to evaluate 3 diagrams with combinations of time-ordered Whitewell and so on, because you already have a 3-fold. When we computed these diagrams, we found it was always 0. And in fact, you can prove that pure contact interactions never contribute to correlators at I naught.
Sorry, I thought there was a relation to the S matrix.
There is a relation to the S matrix, it's real part. Yeah, so it's a real part. So at tree level, the contact interaction never contributes. Of course, at loop level, it does. So you have a 5-4 theory, but tree level, it doesn't contribute. You can prove this in general using CPT. I won't prove it.
And then exchange diagrams will just contribute the delta function.
Yeah, but it's not quite the real part of the S matrix. It's actually something more complicated. It's A dagger plus B dagger. So I'll show you. So it can also be involved terms which are quadratic in the S matrix, as I'll show you. So for higher points, things quickly become complicated. Here's the answer for a 5-point case. It looks like the imaginary part of the T matrix. T, by the way, S is 1 plus IT, so real part of S is imaginary part of T. And here's the other term, as I was mentioning. It also has these terms which are quadratic. And that's because you see, you have to put A dagger plus B dagger, A dagger plus B dagger. And sometimes you get things that are not simply an S matrix, that are products of S matrices. So you can also have T dagger times T, things like this. So it's not just, it's some, it's correlators of A plus B and A plus B, which is not just an S matrix. It could be S matrix. You can rewrite if you know the S matrix, you know all these guys. But it's not just the real part. At lowest order is the real part, but it could also be something more complicated. So for example, let's say you take a theory which has a phi cube plus a phi 4 interaction. Actually, you needed to couple the theory with to satisfy, get something non-zero to some other particle which has a mass m which is larger than small m. Then you could compute this at tree level and you find some simple thing which looks like a sum of delta functions at tree level. And then you can go on to 6 points and higher. I can't, but my collaborators can. They know how to compute this to very high points, and you can compute these things. Okay, so we have done all these computations, and it's some interesting.
So just to be sure I'm understanding, suppose you just had the, I don't know which were the A's, the ones at top or bottom.
Doesn't matter, you can call them. Even I don't know actually. Conventions are confused.
Because you just have one set, the A's and A daggers and so on. Then everything is true.
Then it's a free object.
It's just free object.
And A is on the right and B is on the left is S matrix. Now we have A plus B, A dagger plus B dagger, so that's all kinds of,
all mixed up, but everything can be reduced ultimately to S matrix.
And products of S matrices because because the reason is you might have, for instance, think of this: A plus B, A dagger plus B dagger, A dagger plus B dagger, A plus B, A plus B. Now, what happens is that you get some in states here, but now you've got some in states, and then you have a B acting on the in states. That's not easy. That's not something.
A daggers actually.
Let's call it. Let's use A daggers to be the in state.
Okay.
So now you've got a 2-particle in state.
Yeah. A dagger.
Now you have a B acting on the in state, and you have maybe you might have on the other side also a 2-particle in state. But this is an out operator. So this, what you have to do, you have to insert some complete set of states. That's what we've done then. And then you can evaluate. So you might have things like this. Okay, good. So this is what I want to say. You can have fun with these things.
So
this was
some paper there. The way they get it is that they just consider correlators in some different type of orderings.
Same thing.
And do the put it on shell, right?
This is the same thing that they were thinking of it. This is so.
Effectively, that is what is happening. This is because of the particular ordering that you.
They never wanted to look at half of A plus B. We happened to focus on half of A plus B.
No, but
they were willing to look at arbitrary A's and B's.
Whiteman, correlators, etc. was your choice.
Yes.
It's not like some physical object or some particular meaning that is being associated.
Sorry, I didn't understand. The reason I wanted to focus on Whiteman was because I wanted to define these operators at I0. Yeah. They wanted to say, what if I generally start looking at these things, because they're things you can look at in quantum field theory. Okay. So they found the same answers that we did. My interest is that, I want to define something at I0, and I'm saying the natural things that appear at I0 are these half A plus B, half A plus B. Okay. And it's true, once you know how to compute all these things, you also know how to compute this. So these kinds of expressions measure at all also.
Right. I mean, put this way, you don't seem to be losing any information by percent.
It's not clear because we have imaginary part. It's like this Feynman tree theorem or something you'll have to invoke. If I give you the cuts of the S matrix, do I know the S matrix kind of thing? Maybe.
Is that right? I just
can't
calculate all S matrix elements by suitable combination.
If you know all S matrix elements, you know all of these. We haven't managed to prove if you know all of these. And maybe there is a proof, but we haven't proved it yet.
I thought
there might be. It might well be the case, but we don't.
And then there is the additional question: is if you know all the S matrices, do you know all correlators?
Yeah. Or is there anything else that's left? Maybe all correlators are conventional.
That was the okay. Yeah. So maybe it's just if you know the Whitemans that the delta function supports you.
Same thing. Yeah. Okay, good. I'll stop soon. Let me just say one thing, just to answer Abhijit's thing, because so I didn't forget completely about holography information. This is going to be the paper we are going to put out. Okay, now I'm going to say something about hopes in 1 minute and I'll stop. Okay, so now how do we hope? This is going to go back to the long motivation I gave in the beginning. What is the relevance of this? So I'm going to make a conjecture. It's really a hope. It's not even a conjecture for how we hope that holography of information will work out with massive particles. Okay, so everything I'm saying so far is just a hope. Here's the hope. The hope is consider this algebra of operators, these boundary operators now defined in the interacting theory with this LSZ and so on, and put these smearing functions which die out doubly exponentially. In a non-gravitational theory, this corresponds to the algebra outside a large ball. It's true, as Shiraz will say, there's actually infinite area outside a large ball, but it corresponds to operators outside a large ball. So it misses some information about operators in that ball. Now, think of the, maybe we can also describe massless particles on spatial infinity, but for now, think of the algebra of operators which are tightly focused around the middle of I0, that's this green band, and the operators near the pass boundary of Scri plus, which is this red band. In the non-gravitational theory, this algebra lacks information about a ball in the bulk. The conjecture is that maybe these observables are complete in a gravitational theory. So you write down these observables which are near Scri plus, and these observables which are near the middle of I0. And the hope would be that we could argue that this is complete in the theory of gravity.
Okay, now let me just slow you down. In the non-gravitational case, why did it lack? Just let me get
because you see it
commutes. You didn't have your vacuum projector and all that, but
this just commutes. These operators you can show by microcausality because they're focused. You see, they're focused very close to the center of I0.
So that was the point.
They commute with everything in the middle. They commute with everything close to the bulk.
Okay, so that was the point, that you're just by microcausality.
That's
right. Okay, that makes sense.
Yes. The hope is that once you include the projector and the vacuum and so on, this will all work. We'll have to do a lot more work for that hope. First of all, we'll have to make the story work in asymptotically flat space rather than flat space, and so on. This is just a hope. Okay. I should say hope about it, we're not really doing it. Okay. So as I said, we haven't proved this. This is just a hope. Okay, good. So I'm done. So, my main point was the slogan was, we want to pursue this program that observables at infinity know about observables in the bulk. I think this is interesting for understanding holography, for the information paradox, but it's challenging to understand how to include massive particles in the story. In this talk, I was presenting a representation of massive particles. The representation in the end in the interacting theory was you take the bulk Whiteman function, you do an LSZ prescription that reduces it to Wi0, and then you push it off to infinity, and you have to smear it with these smearing functions. If you do that, you get an algebra of operators, which is an algebra of boundary operators. It's a subtle algebra. You have to do the smearing and so on. But, I think it's an interesting algebra, and it's nicely related to the S matrix. You get, very nicely related to how these operators are diagnosed.
There was K in this algebra. You were doing S matrix.
There was no K. So that was this formula. It was the fact that this Z of F was in fact related to the K this way. So if I told you phi plus K, if you give me a smearing function, I can translate it to the Z of F's. So then I just said I'll just...
There's a map between F and K?
No. F is a smearing function. Remember, Z depends on a smearing function.
Okay.
I have to tell you the smearing function F.
Okay.
If
it's a Fourier transform of...
That's right. So you take pi plus of K, set M since tau equal to K, then you evaluate F at the value tau. Where tau is given by mod of K.
And K
is just the momentum in flat.
Spatial domains.
Mod K is the spatial momentum, yes.
K vector
is spatial. K vector spatial. So you take the mod of that, you evaluate the smearing function at that, but you also have to analytically continue. There's also an analytic continuation.
It's one probably very stupid question. You've got this your operators on some boundary. So it's in 4 dimensions, it's on a 2 space and 1 time dimensional surface.
That's right.
So I can Fourier transform in 2 space to get
that's the
2
L.
momenta.
That's the L. So that's the YL.
Yeah, where do I get the
YL is just YL of K hat. So the direction of K hat gives you the YL of K hat. And then the smearing function also has an FL which determines its
how it's moving in time.
So FL of tau depends how it's moving in time.
And that's where you get mod K from
mod K. Okay, so that's the ZFM. So anyway, this was the final prescription in terms of actually this was So this was the final prescription. So it's subtle but interesting algebra, and then there's a hope of how this will relate to what I said about holography. But this might be an interesting question in quantum field theory. Anyway, I think there's some natural questions about quantum field theory that this might answer. Okay, so that's all I wanted to say. Sorry for going way over time. Thank you very much.
We have had quite a few questions and interactions during the talk, but maybe 1 or 2 more questions.
No, I'm okay. you guys are probably more tired. When you're speaking, you don't feel it. Yeah.
One question. If you did this on timeline, on this timeline part,
at ADS.
Yeah, right. On the CDS, you would very naturally pick up
the S matrix.
Okay. So somehow this feels like this whole process is an analytic continuation.
It could be. Yeah, it's an analytic continuation, except it's not quite an analytic continuation. That's what we also thought, that it would be somehow maybe you take the S matrix and. But it's, yeah, so it's this more interesting thing. We take this half of A plus B. Yeah.
Yeah, but up to those things.
Yeah.
Can that be made precise?
I mean, this is, I think, the most precise thing is that it's half of A plus B. It's kind of somehow the average of these A plus B operators. So it's not quite the S matrix. It gives you these imaginary parts.
So I was thinking, if we were computing action as a function of boundary value from here, and I compute action as a function of boundary value here, there's some relationship between these two things.
So that should somehow give you this. But you see, the relationship is pretty non-trivial, because it's telling you that you're getting the real parts of this S matrix. So it's not just, so somehow, maybe this analysis that you people did, where you looked at these sandwiches, if you were to do it in Lorentzian space by looking at these de Sitter slices, you would actually find that there was this relationship. That would be interesting.
Yeah.
It's a pretty non-trivial relationship, right? Because this A plus B is not clearly the S matrix.
It's like a real part of that.
Real part of what? I mean, something complicated.
Yeah. I ask you really on this line. I was really thinking the Whiteman function can be written as a sum of time ordered and empty.
Sum of lots of different orderings.
Okay, take the 2 point. Just to get going.
The 2 point is yes. The Whiteman plus anti-Whiteman. Actually, it's time ordered plus anti-time ordered is Whiteman plus anti-Whiteman. It's hard to write Whiteman immediately.
Whiteman can't be written as
not immediately, but anyway, but go on with your question. Yeah.
I was wondering, therefore, you could relate these poles of the Whiteman functions to S matrix elements, or time reverse, or some version of this.
It's pretty hard actually to do that directly, because you see, even at 2 point level, it's not so easy, but you can use the fact that the operators are Hermitian and so on to get the time ordered correlator. The Whiteman function you get by taking the Euclidean correlator and by continuing the times from Euclidean to Lorentzian, not all at once, but one by one. You see, if you continue the Euclidean time to Lorentzian time all at once, you get the time ordered correlator. If you continue it one by one, then you get them in the ordering in which you continue them. That's the Whiteman function. And these poles are not in any simple way related to the LSZ poles. You can see that from the perturbation theory also. The perturbation theory involves this n-fold contour. Time-ordered perturbation theory is very simple. It's one contour. So there's no simple way to relate the n-fold contour to one contour. Even for 2 contours, as Loga and so on have explored, the Stringer-Keldysh is not immediately related to it.
Somehow doesn't play nice with analytic continuation. Because you're taking the folds of infinity.
Yeah, LSZ doesn't play nice, but this delta function coefficient is kind of maybe the analog.
Well, that's what I was wondering. There's the delta function parts, but there might be some. Okay.
Yeah,
it's complicated.
It might be, but it's this actually. This A plus B is the best relationship we could find. That's a relationship.
One place where this issue appears is crossing symmetry of S matrices, right? For correlators, all this crossing symmetry, just invoking analytic, you can say. But, showing a crossing symmetry of S matrix is difficult. Because you already be on the board. You are already
so maybe I0 is actually pretty nice for some of these questions, because maybe there's some notion of locality on I0. You can ask questions. So maybe I0 is the right place where you might be able to ask some of these questions. You look at correlators on I0 and they keep track of interactions, and maybe you can ask questions about. It's a little bit like the boundary of EDS, right? It's a cylindrical boundary. So maybe there's something nice about asking correlators of these A plus Bs. They have some information about the S matrix, and maybe you can ask these questions and the bulk point singularity and microcausality and so on. Okay, all these are just hopes, but I don't have.
It feels like bulk point singularity should occur in these operators.
Why not in these operators?
Because you can't propagate on shell to the singular. You can't connect things.
No, you can, no? Because this is this, right? So you can kind of go from here to here. It's really all of this de Sitter slice. You could throw something from here, it could meet, and they could all meet in the center.
all these space-like lines.
Or I'm trying to draw null lines, which is meeting in the center.
No, but we're looking at massive particles. Could you make time like geodesics go and...
No, they're not time like geodesics, but that's not, you see.
Forget geodesics, time like lines go and meet at a point and come back.
No, time like lines you can't, but you could make, but you see massive, okay.
And it's that kind of diagram that gives you bulk point.
Yeah.
So you're saying if you had the ADS parts here and here,
then you would do it, right? That would be that's what we do at
Yeah.
LHC, right?
Yeah. Yeah, okay, that's the S matrix. That's clearly, the S matrix, clearly there's something where you focus particles, so they meet, and something where they miss.
And
So
that's
this is something more subtle. Yeah,
that's the kind of thing that gave rise to bulk point singularities.
Yeah. But maybe there's, okay.
Yeah, but it feels like an analytic continuation. Seems somehow to be like an analytic continuation of that.
Oh, I agree with that, and that's so. It would be nice to rephrase this in terms of directly some analytic continuation of that.
I wonder if something like that. I mean, yeah. If anything like this exists in ADS. So there's a scattering sheet where you get these bulk point singularities. And then you go to some other sheet.
My intuition is constantly driven by.
Right, but there's no. Yeah.
The singularity is the same as.
Okay. Yeah.
Kind of like.
It's kind of, but there's no singularity. The same singularity.
Yeah, but I really want to see this half of A plus B somehow appear. Like this somehow should be something which should appear. Like it should be.
Okay, sounds very interesting.
Okay.
Thank you. Thank you.